Welcome to a quiet corner of the night, where the questions get big and the pace gets slow. Tonight, we're not counting stars or crunching numbers. We're just setting a scene and letting a single idea float to the surface like a lantern on dark water. What if Earth wasn't the first? Not the first blue world to warm in our sun's light. Not the first place to try a breath, a breeze, a beginning. Imagine the solar system as a small neighborhood at the edge of town. You know the houses Mercury's hot porch light, Jupiter's giant yard, yet there's a feeling that a foundation once stood on an empty lot, and the grass grew over the story before anyone wrote it down. We're going to wander that neighborhood together. No heavy jargon, no homework, just a gentle, curious walk. We'll listen for echoes in the dust, peek through the curtains of old worlds, and wonder whether a different home once stood here, lived in for a while, then quietly packed up and slipped away. If that sounds like a lullaby wrapped around a mystery, good. Get comfortable. Let your thoughts loosen like shoelaces. You don't have to believe anything tonight. You only have to imagine. Because sometimes, before sleep, the best kind of science is the kind that starts as a story and asks politely to be considered. Ready? Take a slow breath. Let's see what the night will tell us about the lives our solar system might have lived before us. If you and I were sitting on a porch at midnight with the crickets low and the sky clear, this is the kind of wonder I'd put on the table and let breathe. Maybe the solar system has already tried in Earth once, or twice or more, just not here, not now, not in the exact form we inhabit. The phrase first Earth sounds like a title with only one rightful owner. But what if it's really a job description the neighborhood has offered to more than one world across deep time? To follow that thread, we don't need equations. We need a map in our heads, a few simple ideas, and the patience to let them circle slowly like planets do. Start with the easiest lantern to light. Astronomers talk about a habitable zone, which is the range of distances from a star where a planet's surface could keep liquid water. If you like bedtime stories, it's the Goldilocks porch too close and your oceans boil. Too far and they freeze. Somewhere in between, and you can dip your hand in the bowl and not get burned. That idea is simple on paper and messy in real life, because planets have weather and geology and moods. The sunlight is only the opening chord. A world can warm itself with greenhouse gases. Think of a blanket that traps heat, or cool itself by reflecting light with bright clouds and ice. It can shuffle heat with winds and oceans. It can leak atmosphere to space, or brew a new one from volcanoes. So, habitable zone is a useful phrase, not a guarantee. A common mantra among planetary scientists is, follow the water, and the subtext is even more careful, and ask what the planet did with it. There's another twist that matters for our question. The sun hasn't always shone the same. In its youth, it was dimmer. Scientists call that the faint young sun problem, which is really just a label for a puzzle. Early Earth should have been colder, yet the rocks tell us there were lakes and seas. That means the habitable zone itself drifts over time, creeping outward as the sun brightens. Picture a moving spotlight sliding across the stage. A world that's too hot for oceans today might have been just right long ago. A world that's chilly now may have enjoyed a warm interlude earlier. Suddenly the question, were we first? Spreads out and multiplies. First when? First where? First how? To keep it light and honest, let's define Earth in a wider, kinder way. Not a twin with the same continents and clouds, but any world that could hold on to liquid water long enough for chemistry to get interesting. That definition pulls the camera back. It includes rocky planets like ours, but it also nods to large moons that orbit giant planets, the way our moon orbits us. It even includes worlds with oceans hidden under ice, warmed not by sunlight, but by the kneading pull of gravity. If the habitable zone is the porch, tidal heating heat made by flexing a world's interior is a fireplace inside the house. You can be cozy in there, even when the yard is frost. Before we peek at particular neighbors, It helps to say out loud what planets are. They're not marble statues. They're machines that run on heat and time. Inside, they have cores that cool, mantles that circulate, crusts that crack and heal. Outside, they host winds, clouds, storms, and an invisible magnetic bubble called a magnetosphere, which is a shield built by a spinning metal core that deflects particles from the sun. Lose the shield, and your air gets sandblasted by space. Keep it, and your atmosphere can lounge a while longer. Even that shield lives on a budget. When the core cools too much, the magnet can fade. In bedtime words, planets grow up, they get tired, they change. This is where the idea of earlier Earths begins to feel less like fantasy. If the spotlight shifted, and if different worlds age at different speeds, then the solar system could have offered more than one window where a surface ocean held steady and the air felt kind. The trick is that windows close. A planet can slide into a runaway greenhouse, a feedback loop where trapped heat makes more water vapor, which traps more heat, and the ocean starts to lift into the sky. Or it can thin its air until lakes evaporate and winds sharpen the bedrock. I promised we wouldn't get technical, so keep the image soft. A thermostat, a blanket, and a window that sometimes sticks. One obvious candidate for this earlier window is the world that glows in our sky with a soft gold. A neighbor close enough to hint at family resemblance, and far enough to smell like another story. The cautious way to say it is simple. Some models suggest it once could have hosted shallow seas and gentle rain, before feedbacks pushed it into a thick, suffocating heat trap. That's not a claim, just a possibility that keeps scientists curious. The point for us is the idea, not the verdict. If a world can shift from blue possible to golden blister, then habitability is not a static label. It's a mood swing written in rock and air. Another neighbor wears a red coat and a quiet expression. It's small, old, and scarred, yet its valleys and deltas whisper of flowing water in the deep past. Rover wheels have nudged pebbles rounder than wind alone would make. Minerals that form in lakes have been found where lakes once sat. Once upon a time, this is the soft truth. The red world had a thicker atmosphere and warmth enough for rivers, at least in bursts and seasons. It doesn't have that now. Its magnetic shield faded early, and its air escaped in tiny spells over ages. The lights dimmed, the lakes withdrew. If you're keeping score, that's strike two for the idea that Earth is a permanent condition. Worlds can visit that state and move on. But the porch light and the fireplace aren't the only ways to keep a room livable. Farther out, past the snow line, the distance where water prefers to be ice live, moons that hide whole oceans beneath crusts. The phrase subsurface ocean sounds clinical. In story terms, it means a sea in a cave, warmed by the kneading of tides from a giant planet's gravity. One moon has been seen spraying water vapor and ice grains from cracks at its south pole like a garden fountain. Another shows a surface that looks like cracked sea ice on an Arctic river, jostled and refrozen. On these worlds, life, if it ever sparked, would be more like the life that thrives at deep-sea vents on Earth, where chemical energy feeds ecosystems in the dark. Sunlight is not the only menu, as one oceanographer likes to tell her students. That sentence matters for our question. If first Earth simply means first stable home for complex chemistry, these hidden oceans could have been in business while the inner planets were still dodging big rocks. That phrase, dodging big rocks, points to another chapter the solar system lived through. In its unruly youth, leftovers from planet building pinged around like marbles, sometimes crossing paths with dramatic consequences. You don't need the details to hold the shape of it. Collisions big enough to melt crusts happened. Smaller ones, big enough to scorch the sky and boil lakes, kept happening long after. Some researchers once proposed a late heavy bombardment, a period of especially rapid impacts, though the exact shape of that story is still being refined. The bedtime version is safe. Early on, the neighborhood was loud. Any first Earths that tried to brew a calm surface had to wait out the worst of that rain. That waiting game didn't only happen outside of us. Our own planet wore different faces. There were chapters of deep global cold called Snowball Earth, when ice reached low latitudes. There were intervals warm enough that crocodiles swam in polar seas. There were chemical revolutions in the air, including a rise in oxygen made by tiny organisms learning how to sip sunlight, a turning point sometimes called the Great Oxygenation. I'm not naming those to make a list, just to share a feeling. Stability is rare and miraculous. If we find it dull, that's because we live in the middle of it. When scientists look for earlier moments of Earthness around our sun, they're looking for evidence that a world could maintain surface water long enough to give chemistry time to braid into life, and maybe long enough for life to braid into complexity. You don't have to picture skyscrapers. A thriving microbial ocean is already a spectacular success. The hard part is time. How many millions of years does a planet get before the thermostat sticks, the shield fades, or the sky tips one way? We don't have that answer for every world. We have hints and scars, and a shared method that feels like detective work. A planetary scientist once described it like this: we never get the whole diary. We look for coffee stains on the page. Those stains have personalities. An ancient shoreline leaves a curve of pebbles the size of your thumb. A lakebed leaves clay minerals that only form in water. A passing ocean leaves a hint in the ratio of heavier and lighter versions of hydrogen locked in rock. Because light atoms escape to space more easily, and the leftovers grow fractionally heavier, like a soup that thickens when steam leaves the pot. You don't need to remember the chemistry to feel the comfort. There are footprints that last longer than feet. They're subtle. They're not the kinds of monuments bedtime stories promise, but they're durable and they're fair. Once you accept that, the question, were we first, becomes generous. It doesn't accuse. It simply asks whether the coffee stains on another world's page line up to spell weather mild enough, long enough for an ocean to daydream. Scientists argue about the details because that's what honest curiosity sounds like up close. One researcher's possible shallow seas is another's probably not for long. That bickering isn't failure. It's the small engine that keeps the big one honest. The quiet truth underneath is shared. Planets are more flexible than our first guesses, and time is longer than our patience. There's one more gentle complication, and it helps us stay humble. Earth-like isn't only about water and warmth. It's also about a planet's interior life. Our world reshapes its own surface through plate tectonics, the slow shuffle of crustal plates driven by heat from below. That process recycles nutrients, builds continents, and may stabilize climate over long spans by balancing how carbon moves among air, ocean, and stone. A world without that shuffle might stall out too much carbon in the sky and you overheat, too little and you freeze. In simple terms, geology is a partner to weather. Whether a world danced that dance early, and for how long, is a deep part of whether it could audition for first Earth. We can hold that thought lightly without letting it weigh the story down. The takeaway is not the rules are complicated, but the opposite. The rules are simple, and the consequences are complicated. Put a rock the right size, the right distance from a modest star. Give it some water and a bit of greenhouse blanket. Make sure it can hang on to its air and bleed off its heat. Step back for a few 100 million years and see what the kitchen cooks. That's how understated the recipe is. And it's why the solar system might have set the pot to simmer on more than one stove. You might be waiting for a grand reveal, but this isn't that kind of dream. It's the kind where you stroll through rooms and notice how the light falls. We've noticed that one neighbor may have started warm and swung hot. Another seems to have opened the curtains to rain and then pulled them shut. Farther out, moons may have ignored the sun entirely and gone swimming under ice. If a child asked whether those count as Earths, I'd nod and say they count as auditions. Some sang a verse, some lost the melody. A few might still be humming beneath the ice, their voices soft enough that we haven't yet learned to hear them. The nice thing about this porch conversation is that it nudges us toward our instruments without scaring the sleep away. When a spacecraft maps the chemistry of a rock, it's listening for that hum. When another dips a sensor through a plume of water and tastes the salts and the organics, the building blocks of life, it's reading the menu by feel. When radio dishes ping a world's magnetic bubble and learn whether it has a shield, they're asking if the front door can stay shut in a storm. None of those actions prove a civilization, or even a fish. They simply say, in patient stone letters, conditions here were not impossible. The older you let that sentence grow, the more it answers the title we started with. Could there have been another Earth before ours in the solar system? The most careful answer is the most romantic one. Yes, in the sense that multiple worlds likely enjoyed stretches of temperate grace before we arrived, and some may enjoy them still. Whether any of those stretches lit the tiny, stubborn spark we call life is another question, and the night is big enough to hold it until morning. The important thing for a sleepy mind to keep is that our planet's story is not the only way this neighborhood tries to be kind. The porch light moves, the fireplace burns. Sometimes the house is warm in a room we haven't stepped into yet. There's kindness in that view of things. It takes the pressure off us to be the only act and lets us be one verse in a longer song. It gives us a way to love our place without needing it to be unique in every way. It even gives us a reason to explore that feels like a lullaby rather than a dare. We're not hunting for trophies. We're visiting old neighbors and asking how their days went. Did they have rain? Did they keep their shield? Did they try a sea in a cave and like it? Before you drift, tuck one last idea under your pillow. The evidence we'll talk about as we go, the stains, the ratios, the pebbles and plumes, isn't about proving legends. It's about learning the temperament of worlds. If we can learn that, then whether or not anyone came before us, we'll have done something tender and precise. We will have listened quietly to the way planets speak when no one is watching. All right lights low, shoulders unclench, and let's wander further into the what if. We've asked whether Earth could have had an older sibling in spirit, a world that wore oceans, made weather, maybe even hosted thinking creatures. Now let's widen the frame and move through the neighborhood without getting tangled in equations. Think of the solar system as a row of old houses on a windy street. Some have fresh paint, some have boarded windows. Some look normal until you step closer and notice the cracks. Our job tonight is not to prove anything, but to walk that street slowly and ask, house by house, what stories the paint might be hiding. Start with the idea of habitability, which is just a fancy way of saying, can this place hold liquid water at the surface for long enough that chemistry has time to get weird in a lively way? The classic picture is a Goldilocks zone, the distance from a star where a planet isn't too hot or too cold. But that's just the front door. Inside the house, you need insulation, ventilation, and plumbing. On a planet, those become an atmosphere that traps heat without cooking it, a magnetic field that deflects charged particles, and geology that recycles nutrients. When astronomers say greenhouse effect, they mean the blanket of gases like carbon dioxide and water vapor that keep heat from escaping too quickly. A little blanket is good. Too many blankets and you can't breathe. Too few and the room freezes. That's the line Venus and Mars crossed in opposite directions. Venus is the warning label. Same size as Earth, near enough to tempt poets, and wrapped in a runaway greenhouse. A positive feedback loop where more heat releases more greenhouse gases, which trap more heat. Surface pressure, there is the weight of an ocean stacked on your shoulders, and the air is acidic enough to chew metal. But peel back the present, and there's a strangely Earth-like hint. High above the inferno, the clouds hover at temperatures and pressures not too different from our mountaintops. Some scientists, remembering that life only means self-sustaining chemistry that copies itself with variation, have asked whether the upper clouds could have once been a refuge. Not a city in the sky. Don't picture zeppelins, more like droplets that carry microbes, the way dandelion fluff carries seeds. If that ever happened, it would have been brief, fragile, and almost impossible to prove from here. Still, the idea keeps showing up because it reminds us how quickly habitable can flip to hostile. Mars is the heart-tugger. Dry riverbeds, delta fans, minerals that only form in standing water. It's like walking through a drained lake and seeing the shoreline traced in the mud. Billions of years ago, Mars wore lakes and maybe shallow seas. It likely had a thicker atmosphere and a magnetic shield. Then it cooled, the shield weakened, the solar wind eroded the air, and the water either escaped or hid underground as ice and brine. If anything complex ever stirred there, it would have lived small, subsurface, shielded from radiation, breathing the chemistry of rocks the way cave microbes do on Earth. If you're imagining ruins, slow down. Even on Earth, stone erodes and metal rots. On Mars, dust storms, temperature whiplash, oxidizing soils artifacts would fare worse. What's realistic is chemistry. Isotopic ratios that lean the wrong way, layered sediments that speak of sudden change, minerals out of place. Nature writes in clues, not confessions. As a planetary geologist once quipped to a room of sleepy grad students, that's our vibe tonight. Beyond the old inner worlds, the outer system looks like a freezer that forgot it was a pantry. Jupiter's moon Europa and Saturn's Enceladus are wrapped in ice. But crack the shell, and you find global oceans kept liquid by tidal heating, which is the gentle kneading a moon feels as gravity flexes it. If habitability is a recipe, these moons have the wet ingredients ready to pour. Does that matter to our question? Only sideways. It says life might not need a sunlit surface or a mild sky. If oceans under ice can be alive, then a planet that looks dead from orbit could be bustling below. Translate that back to early Earth or to Mars long ago, and the moral is simple. Surface impressions mislead. Now zoom into the young solar system when everything was louder. There was more debris, more collisions, more heat, more chemistry swirling through impact craters and volcanic vents. Astronomers call this heavy bombardment, and you can hear the tone in the words. In a storm that violent, how does complexity even get a footing? One answer is that storms don't last forever. The sun calmed, orbits settled, water pooled and lingered. If you give chemistry time and gradients hot to cold, acid to alkaline, it tends to climb little ladders all by itself. That ladder climbing is what biologists mean by metabolism. A simple version is rust. Electrons move, energy flows, things change state. A fancy version is you, listening right now, moving energy and matter gently through a brain. Suppose some other world climbed a similar ladder before ours did. How would we know? We wouldn't be looking for statues. We'd be looking for disequilibrium, a word that sounds like a mood, but really just means the environment is out of chemical balance in a sustained way. Oxygen in Earth's air is disequilibrium. It shouldn't be so abundant unless something keeps making it. On a planet with no life, gases tend to settle into truce. With life, they bicker constantly. That bickering leaves signatures. The trick is that volcanoes and impacts leave signatures too. So our detective kit is really a series of could-be meters. Carbon isotopes skewing light, could be biology, could be methane burps from the deep, a sudden warming spike, could be industry, could be a buried carbon pulse from a giant swamp lit on fire by tectonics. Bring this home with a thought experiment. Imagine Earth went through an early industrial moment we never met local. Brief, smarter than campfires, but nowhere near global. Would anything from that moment still be legible after 200 million years? Most likely no. Metals would oxidize. Plastics would photodegrade unless buried. Concrete would fracture and mineralize into something geologists would label with a calm Latin name. What might persist are thin, weird lines in lake beds and sea mud, a drift toward lighter carbon, a dusting of industrial minerals, a blip of nitrogen compounds beyond what storms and lightning alone explain. That's not proof. That's a raised eyebrow. Science, being a careful sort of storytelling, needs more than eyebrows. The good news is we've gotten better at finding eyebrows. We can read the history of ancient climates from microscopic shells, each band a tiny diary entry about temperature and acidity. We can sniff atmospheres of exoplanets' worlds around other stars by watching how starlight changes when a planet passes in front of it. We can fly through plumes jetting from an icy moon and test what's in the spray. None of this guarantees answers about our own past, but it tunes the instruments. You get good at your home world by practicing on others. A mission scientist said after a long night of analyzing data that looked like static to everyone else. It's like learning a language by eavesdropping. Eventually, the murmurs take shape. If the question is whether another Earth existed in spirit before ours, there's also a more radical path to consider. What if the earlier intelligence didn't look like us, didn't build durable things, didn't even think in the way we map with words? Termite colonies air-condition their mounds. Slime molds solve mazes to find food. Coral reefs engineer cities out of sunlight and calcium. These aren't civilization as we define it, but they're organized systems that reshape their environments. Scale that up in time and subtlety, and you could imagine a lineage that learned to live lightly on purpose, an intelligence that found permanence in cycles rather than in monuments. If they succeeded, their invisibility would be the point. We keep equating advanced with leaves a mess. Maybe that's a bias we'll outgrow. There's a romantic temptation here to turn every anomaly into a message. A groove in a stone sphere becomes a machine mark. An odd mineral seam becomes slag. Most of the time, nature wins those debates on appeal. Rocks weather into tricks. Mines collapse and mix. Layers slip. Samples get contaminated. Skepticism is not the enemy of wonder. It's the style guide. So the invitation tonight isn't to believe. It's to hold the door open. Keep the bar high, but keep the door open. If 5 faint hints line up in one narrow slice of time across the world, maybe we go back with finer tools and quieter egos. Meanwhile, the solar system keeps teaching humility. Mercury is a bruised cue ball of a world, scorched and quiet. The moon, our own loyal tidemaker, is a scrapbook of impacts and lava plains. Tiny Ceres in the asteroid belt shows bright salt patches like eye glints. Pluto, far and cold, wears rusty hearts of organic frost. None of these are second Earth, but all of them complicate the old, tidy map. They say, chemistry is creative. Time is long. Surprises are normal. If you asked 10 scientists off the record where they'd bet on unambiguous signs of prior complexity, most would still pick Mars' subsurface, ancient, modest. If you asked the same 10 where they'd bet on something truly weird, you'd hear more scattered answers. Cloud tops of Venus, briny streaks on Martian slopes, the dark dunes of Titan, where methane rains like a petrochemical spring. Curiosity thrives in those splits. This is also a story about scale. Human brains are excellent at decades and mountains, bad at millions of years and continents that move like slow dancers. But deep time is the canvas for this question, and on that canvas, erasure is constant. Oceans are conveyor belts, dragging seafloor down into the mantle to be melted and remade. That process is called subduction, and it's why the oldest ocean crust is young compared to continents. If any early coastal civilization existed on Earth, most of their coastlines would have been recycled already. That fact doesn't prove anything except how narrow our search window is. It's like looking for a note on a desk that's been tidied every hour for 1 billion hours. Sometimes the right way to hold a mystery is to flip it. Imagine future beings reading our layer. They'd find a carbon spike, plastic dust, fly ash particles, odd minerals, and a whisper of radioactive isotopes from mid-20th century tests. They'd infer a burst of industry, a compression of change into a geological instant. But if they looked for cities first, they'd miss it. The chemistry would tell the story better than the ruins. That's the lesson we can borrow moving backward. Focus on the chemistry first, the artifacts later. It's less romantic. It's more realistic. There's a gentle consolation in all this. Whether we are the first or not, the act of asking connects us to whatever else has wondered here. It's the same impulse that makes a kid look under a rock for beetles, and an astronomer stare at a dim pixel for 6 hours. We don't just want answers. We want company. Searching is a love language. An astrobiologist once told me, half joking, half not. Maybe that's why this question makes such good company for sleep. It's a low, steady hum. It doesn't demand a conclusion. It just sits beside you like a friend who knows how to be quiet. So the neighborhood stands. Venus with its bright curtains and hidden furnace. Mars with its empty riverbeds and locked door cellars. The icy moons with their oceans and soft buzzing of chemical possibility. Earth with its loud present and missing pages. Could there have been another Earth before ours? Not in rock and radius, but in story and spark? The honest answer is maybe, and that maybe is big enough to house wonder without evicting reason. We don't have to choose between bedtime mystery and grown-up method. We can carry both the way a hiker carries a map and a camera, one to keep us from getting lost, the other to make it worth the walk. Where we go next is closer to the ground and a little more personal. We'll step away from planetary tours and talk about what survives, what doesn't, and how patient a planet can be when it decides to file things away. For now, breathe. Let your shoulders drop a little more and keep the door open a crack for possibilities that don't fit neatly on a diagram. The street is long, the houses are old, and the night is on our side. If you want to hide something forever, you don't drop it into a vault. You leave it on Earth and give it time. Not a human lifetime, not a shelf life, but time in the measure the planet prefers. Ages, not years. That's the thin, unsettling truth behind our question tonight. Even if another round of complexity flickered here before us, the archivist in charge is geology, and geology is less a librarian than a compost heap efficient, thorough, and serenely uninterested in our attachments. Start at the surface, where everything feels solid underfoot. That feeling is a magic trick. Rock is brittle when you kick it, but over long spans, it flows. Mountains behave like bread rising and sagging in a slow oven. Basins fill and empty. Coastlines redraw themselves as if someone misplaced the original sketch. The engine beneath this shapeshift has a lyrical name, plate tectonics, but it's really a simple idea. Earth's outer shell is cracked into rafts that drift on warmer, softer rock. Where they pull apart, new crust blooms like fresh crust on a pie. Where they collide, one slab often dives under another and vanishes into heat. Geologists call that subduction, and it's the planet's delete key. Ocean floors, where so many cities and stories like to gather, get fed back into the deep over tens or hundreds of millions of years. The oldest seafloor on Earth is young by the planet's standards, which means the most likely places for earlier coastal lives to have breathed are also the places most certain to have been recycled. Above that slow conveyor belt, weather works like a tender, tireless sculptor, shaving, prying, dissolving. Rain isn't just water, it's a weak acid. Frost doesn't just sparkle. It paws open small seams into big ones. Roots creep in with patient strength and make rubble of what we thought unbreakable. Even our proudest materials lose their temper here. Iron returns to dust. Copper blooms green. Concrete allows water in, swells and fractures. A modern skyline looks invincible in daylight, but leave it unmaintained, and in a few centuries, it becomes a sketch. In a few millennia, a rumor. In a few million years, a smear of unusual minerals in a layer a future geologist will label without ceremony. Nature writes in clues, not confessions. As one field geologist likes to say, brushing dust off a sample bag. Now and then, the planet accelerates the edit. Volcanoes repaint entire regions in an afternoon, and then spend centuries weathering into fertile soil. Glaciers arrive like slow, blind carpenters and plane the landscape flat, carrying away what stood there before and dropping it as a scattering of unsorted stones called till. Rivers meander, cut their own oxbows, and bury the old channel with new silt. The same way, a story told often learns to forget its early drafts. Wildfire leaves charcoal and a brittle memory, which wind and rain rearrange into patterns that look like meaning until they don't. An impact from space can reset the stage altogether, not only with the blast, but with the rain of melted rock that follows, a hailstorm of glassy droplets that settles into a crisp line in the rock record, easy to spot, rarely verbose. We love to think the ground is a book. It is, but most of the pages are missing, and the ones that remain were rebound, scorched, soaked, and copied over. The gaps have a name: unconformities, and they are everywhere. Stand at the rim of a canyon, and you can place a fingertip on a ledge where 100 million years go missing between layers. What happened in that interval? Perhaps everything. Perhaps nothing that left a mark. The absence doesn't argue. It just sits there, a calm shrug in stone. This is why fossils feel miraculous. To become one requires luck stacked on luck. Something dies in a place where scavengers or rot can't scatter it. Sediment arrives quickly enough to cover and protect it. Minerals in groundwater infiltrate bone or shell, replacing the original with a durable cast. Later, the overlying rock survives long enough to be lifted and eroded just enough to expose the treasure, and then a pair of curious eyes happens by before the sun or frost or boots turn it to powder. For every fossil on a museum mount, imagine a parade of ghosts that never had the chance. Even with bones, survival is the exception. With tools or buildings, the odds are worse. So, what could endure from a civilization old enough to have shared the sky with ancient seas or early forests? Not the things we intuit first. Roads peel, towers fall, looms and books and wires return to the elements that made them. Even stone loses its edges. What does last are the planet's stubborn little bookkeeping marks, ratios of isotopes, versions of elements that differ by weight shifted in ways that suggest someone burned, smelted, fermented, or fertilized more than volcanoes and lightning would explain. Tiny shards of ceramic or glass, tucked safely in an anoxic mud at the bottom of a quiet lake. A vein of metal with the fingerprint of refining rather than geology. A thin horizon in a core sample where abundance and variety of microfossils falter all at once, as if something upstream nudged the web of life and it rang like a bell. Even those are not smoking guns, but raised eyebrows. Volcanoes can fake an industrial sky. Methane seeping from frozen clathrates can mimic the breath of farms or factories. Rivers can smear the chemistry of a distant mine across a wide delta, and millions of years later, you'd read the smear, not the hand that made it. That's why scientists lean on convergence. One anomaly is an oddity. Several, stacked in the same slice of time around the world, begin to whisper a pattern. Extraordinary claims need a choir, not a solo. A geochemist once told a room of students, trying to decide whether their sediment spike was a proxy for climate or a lab artifact. The wisdom lands softly here, where we're trying to balance invitation with restraint. We're not here to smuggle Atlantis into a lab coat. We're here to behave like careful listeners. Time complicates even our best instruments. The longer a signal sits, the more it diffuses, blurs, or is overwritten. Pressure and heat can metamorphose a sedate limestone into a sparkling marble, and in the process scramble the fine print. Buried lake mud turns to shale. Shale, cooked deeper, becomes slate. Slate, pushed and kneaded, becomes something else again. Each transformation is both survival and amnesia. The rock persists. The story softens. What remains legible after such a journey is whatever the planet considered important enough to preserve by accident. There's a kindness tucked in the gloom here. If the Earth erases, it also occasionally seals. In desert caves where air is dry and still, textiles can persist for millennia. In peat bogs, chemistry slows decay to a crawl. In deep, oxygen-poor ocean basins, fine dust settles in calm. Thin layers like winter on a quiet lake, year after year, making a barcode that a future drill can read. If there had been a moment of unusual activity industrial, or otherwise across a region, some of those calm basins might have trapped a whisper of it. It's not flashy, but then truth rarely is. It files itself away modestly, expecting us to do the work of noticing. The work is never just in the field. It's also in the questions we carry. If we look only for monuments, we'll miss the chemistry. If we demand a statue in granite, we'll turn away from a slender line of altered soot in clay. That's the discipline this topic invites, especially in a format meant to cradle sleep. Hold the possibility like a feather, not a gavel. Allow that the planet could have hosted more than one attempt at complexity, and also that it might have tidied almost all of it out of sight. There's a small, practical coda to this meditation. Whatever we leave behind will be read the same way, not by our poems or our skyscrapers, which are temporary fancies, but by our unintended geology, the thin, bright seam of plastics, the gentle tip of carbon's isotopes, the out-of-place minerals that once were concrete and fly ash. If someone far ahead ever wonders whether we were here, they'll find us as a narrow band and a few durable crumbs. That knowledge isn't a scold. It's a softness, a reminder to enjoy the hours we do have on the surface and to do our work with a little humility. For our purposes tonight, the takeaway is simple and strangely comforting. The Earth is a great eraser and a selective scribe. If an older story lived here, it may be gone in the ways we most crave and present only in the ways that demand patience. That doesn't make the story less real. It makes the act of listening more deliberate, more human, and if you let it, more soothing. We don't need certainty to rest well. We need a roomy maybe and a planet under us that hums with old, honest work. If the continents are a house, then the continental shelves are the wide front porch, the shallow ledges that ring our lands before the floor drops away into the deep. For most of recent Earth history, that porch has been busy. People love shorelines, mild weather, steady food, quick travel. But shorelines move. When ice sheets grow, oceans fall and the porch widens into broad plains. When ice sheets melt, seas rise and the porch goes under. Over the last 20,000 years, the ocean climbed more than 300 feet, enough to drown entire river valleys, deltas, and lowlands that once were dry ground. Think of farms, villages, and footpaths gently handed to the sea, not all at once, but tied by patient tide. That image matters for our big question. If you wanted to hide the traces of a civilization without lifting a finger, you'd build it where most civilizations naturally prefer to be, on that porch. The sea, kind as a cradle but ruthless as an editor, will take care of the rest. Salt water is busy chemistry. Metals corrode fast. Wood swells, then rots. Ropes and fabrics soften to rags, and then to nothing. Waves abrade edges to pebbles, pebbles to sand, sand to silt. Burrowing creatures worms, clams. Crabs stitch and churn the upper layers of seabed in a process scientists call bioturbation, which is just a tidy word for the seafloor gets stirred like batter. Neat patterns become noise. A few definitions help here. Continental shelf means the broad, shallow border of a continent that stays under 200 meters or so of water before it. breaks sharply downward at the shelf break. Beyond that rim lies the steep continental slope, and then the abyssal plain, the true deep ocean floor. Anoxic describes water or mud short on dissolved oxygen conditions that slow decay and sometimes preserve fragile things. Bathymetry is underwater topography, the mapping of depths and shapes across the seafloor. Put these together and you get a picture. Most of what we'd want to study old shorelines, drowned river mouths, ancient harbors sits in a narrow, shallow ring that's chemically hostile to preservation and mechanically restless. It's not impossible, just unhelpful. Every now and then, the sea does us a favor. A storm collapses a cliff and buries a site in a quick blanket of sand. A delta shifts, sealing a channel in mud. In the dark, quiet bottom of a bay, an anoxic layer forms and turns organic litter into a time capsule. Under those rare conditions, wood can last centuries, even millennia. A clay jar might keep its shape. A shard of ceramic-baked clay, turned almost to stone, can endure far longer. Ceramics and glass are stubborn survivors, our best candidates for accidental immortality on a shifting coast. If a diver finds patterned pottery where no geology could have made it, the story begins to sharpen. But you still need a map, a context, a cluster of clues strong enough to drown out coincidence. Mapping is its own challenge. We've charted the moon more finely than most of our shells. Sonar sound pulses sent to the bottom and timed on the return sketches ridges and hollows, but at a resolution that often blurs small, human-scale shapes. To really see, you need high-frequency sonar sweeps, magnetometers to sniff out buried metal, and cores long, thin cylinders of mud pulled from the seabed to read layer by layer. Each core is a diary. Grain size changes hint at storms. Pollen grains drift in from land and whisper which plants were growing. Tiny shells of marine life, called foraminifera, hold chemical hints of past temperature. Every line is a sentence. Every abrupt shift, a plot twist. Sediment remembers quietly, one marine geologist says. We just have to ask the right questions. Even a good diary has limits. Shells are highways for sand. Storms and currents push sediment sideways for miles, smearing local signals into regional averages. That blurring is useful if you're hunting for global events, a climate jump, a sudden flood of nutrients, but not if you're hoping to spot a small harbor wall or a cluster of posts that once framed a pier. Geometry, the straight line, the right angle, the repeating grid helps, because nature prefers curves and fractals. But limestone can fracture in neat patterns. Basalt can cool into columns that look designed. Without companions, tools, pottery, processed metals geometry can mislead. And then there's the cruelest piece of the ocean puzzle. Time on the seafloor is short. The average age of oceanic crust, the hard basalt beneath the abyssal plains, is only about 200 million years. That sounds vast until you remember the Earth is 4.5 billion years old. Why so young? Because the ocean floor is born at mid-ocean ridges, where hot rock wells up and freezes into new crust, and it dies where plates dive back down into the mantle at trenches. Subduction is the conveyor belt's end. Over spans of deep time, the seafloor is recycled wholesale. Anything that once sat on its sediment, shells, shipwrecks, cities rides the slab downward, heats, deforms, and disappears. The shells, being part of the continents, last longer, but they too are constantly reworked by erosion, river delivery, and sea level yo-yoing. The porch is sturdier than the driveway, but it still gets repaved. If this all sounds like a polite way of saying good luck, it partly is, but difficult isn't impossible. We already read drowned landscapes in remarkable detail when we know where to look. Submerged river channels show up as sinuous trenches in sonar images. Ancient shorelines appear as subtle steps cut into the seafloor, called strand lines, like ghost beaches stacked below the modern one. In the North Sea, Teams have reconstructed lost plains and marshes where people once walked when the Ice Age oceans sat lower. Off many coasts, archaeologists have found stone fish traps, pilings, and pavements built when sea level was yards below today's. None of these reach back millions of years, but they prove the method. With patience and the right tools, the porch can talk. What would count as a louder whisper from deeper time? A widespread, thin layer on multiple shelves with the same odd ingredients. Tiny glass spheres from high-temperature processes unrelated to volcanoes. Ceramic dust, a global pulse of certain industrial metals in ratios that don't match natural erosion. A line of altered carbon isotopes, not just lighter or heavier, but changing abruptly in step with those other markers. Perhaps even synthetic molecules, long-chain polymers that nature rarely assembles, trapped in fine-grained muds within bays and inlets. None alone would be proof. Together, repeating across oceans in the same narrow slice of sediment, they'd start to look less like weather and more like behavior. We also have to build in a kind of humility about scale. Our own coastal footprint, if abandoned today, would be ferociously edited. Subways would flood within days. Ports would slump. Boardwalks would rot. The most persistent debris would be what we didn't mean to last. Landfills armored in clay, ceramics scattered like seeds, a fog of microplastics settling into estuary mud. 1,000,000 years from now, most of our waterfront would be gone. What remained might be a chemical accent unmistakable if you know the modern baseline, confounding if you don't. That's the subtle trap of looking backward without a guide. Even clear signals look like puzzles when you don't know which picture the pieces belong to. Here's a softer thought to hold as you drift. The ocean is not an enemy of memory so much as a curator with strong taste. It favors patterns over objects, chemistry over architecture. It erases clutter and leaves rhythm. If an older civilization ever brushed the shorelines of this world, its best shot at whispering to us now would be in that rhythm synchronous changes, quietly pressed into mud all around the planet's rim. Our task isn't to force a story into that rhythm, but to keep our ears tuned to it, to let data pile up until a melody, if there is one, emerges on its own. A paleoceanographer once described the work this way. You never find Atlantis. You find a thin gray line, 10 centimeters down in a core, and you realize the planet hiccuped there. Your job is to ask why without getting romantic. That's the balance we'll try to keep curious, not credulous. Calm, not cynical. The porch is wide, the sea is patient, and somewhere in that quiet, layered ledger might be a page with a smudge that doesn't belong. If oceans are the world's shredder, a few rare places behave like lockboxes' quiet environments that keep secrets far longer than the noisy surface. Think of them as geological vaults. They don't preserve everything, and they don't preserve it perfectly. But compared to coasts and open ground, they're surprisingly kind to fragile traces. If a not quite first Earth ever flickered here before us, these are the rooms where a whisper might still be audible. Start with lake bottoms, especially the calm, deep kind that form natural settling ponds. In certain lakes, sediments arrive in thin, annual layers called varves, light band in summer, dark band in winter, like a tree ring you can unroll, because the water at depth can be cold and short on oxygen. Anoxic, meaning microbes that chew things up, are sluggish organic bits don't vanish as fast. Pollen floats in from the shore. Dust drifts from faraway deserts. Microscopic shells from plankton with names like diatoms and foraminifera carry chemical memories of temperature and nutrients. Pull a core from that mud, and you get a slow, careful diary. Not a novel with characters, but a ledger of changes. A lake is a quiet accountant, one paleontologist joked. It doesn't gossip, it just keeps the books. If a civilization made fertilizers, cleared forests, or released odd compounds, those lakes could log the shift as a sharp, narrow accent in the otherwise steady rhythm. Peat bogs are another vault. Peat is partially decayed plant matter piled in soggy places where water keeps oxygen low. Bodies, wood, woven fibers, even butter can survive for millennia in bogs because rot never quite gets going. Tannins, the same chemicals that tan leather, seep from moss and darken everything, slowing microbes like a natural preservative. A wool cloak or a fragment of twine might endure in a bog far longer than on open ground. Scale that chemistry to deep time, and the odds still aren't great the planet eventually dries. Floods, burns, but bogs buy time. If a culture leaned heavily on plant fiber, woven mats, baskets, or bark cloth, a bog is one of the few places where a scrap might last long enough to fossilize. It won't tell a whole story, but a patterned weave is not a rock's idea. Salt can be an even more stubborn archivist. Evaporites are minerals left behind when water evaporates halite, rock salt, gypsum, and friends. Deposits form in desert basins or landlocked seas. Salt loves to entomb. A leaf, a bug, a wood chip can end up sealed in crystals, moisture pulled away so thoroughly that decay stalls. Some salts flow under pressure. They're plastic, which can distort or bury whatever they hold, but they also isolate. A pocket inside a salt bed is like a time capsule with the power turned off. The catch is access. Salt domes in basins are often deep and deformed. You don't stumble into one with a shovel. Still, if any synthetic microparticles, unusual polymers, engineered pigments ever found their way into a drying basin en masse, a future core might trap them like confetti in glass. Tar pits, the asphalt seeps, geologists perform work differently. Sticky petroleum oozes up, animals step in, and over centuries, bones pile into a rich, dark stew. The chemistry keeps oxygen away, minerals infiltrate, skeletons persist. That's great for teeth and bone microstructures, less great for textiles or paper. But even a tar pit leaves chemical fingerprints in the surrounding sediments, heavy hydrocarbons, odd ratios of certain elements. If an industrial process concentrated metals or released complex organic compounds, localized asphaltic basins could hold a denser, more decipherable signal than open ground. Caves might be the world's most underrated safes. In the slow drip of limestone caverns, dissolved calcium carbonate precipitates into speleothems, stalactites, and stalagmites that grow millimeters per century. As they form, they trap trace chemicals from surface water, including dust from fires, pollen, even aerosols from industry. Geochemists read these like ice cores in stone. A cave wall can also host speleothems of record, thin, shiny flowstone sheets that lock in decade-to-century pulses. A cave is a slow printer, a cave scientist once told me. Feed it climate and chemistry, it spits out stripes. If any synthetic molecules made their way into rainfall for a sustained spell, say, fluorinated compounds or microplastics small enough to travel with aerosols, some caves would file that away, stripe by stripe. Then there are lava tubes, hollow tunnels left behind when the skin of a lava flow hardens and the molten interior drains. They can be dry, cold, and stable for long periods, protecting whatever happens to fall or be stored inside. On Earth, most are volcanic young in geological terms. On other worlds, High, Moon, and Mars, they may be prime shelters. On our planet, a tube could keep artifacts intact for tens or hundreds of thousands of years. Millions? Unlikely unless later lava or landslide sealed the vault. Still, as natural bunkers, tubes are one of the few places where geometry right angles. Repeated spacing might survive erosion's constant nudge. Permafrost ground that stays frozen all year deserves mention too. It's a freezer for DNA, wood, and even soft tissue. The problem is that permafrost zones migrate with climate. Over millions of years, frost lines come and go. Tonight's freezer is tomorrow's sponge. For our deep question, permafrost is a short-term vault. brilliant on the scale of ice ages, poor on the scale of epochs. A quick glossary for the road. Diagenesis is the suite of changes that sediments undergo after burial compaction. Mineral swap-outs, cementation. It's how loose muck becomes rock, and it can both destroy and preserve clues. Concretion is a local cementation blob of hard, usually rounded lump that grows as minerals precipitate around a nucleus. Concretions can mimic artifacts, perfect spheres, buttons, disks, and fool the eye. They're nature's prank. A lag deposit is what remains after finer materials wash away. Heavy bits like pebbles, shells, or slag concentrate at the surface. Lags can preserve clusters and patterns, but they're also remixers artifacts out of original context. So, how would we use these vaults without fooling ourselves? One principle: triangulation. A single odd reading in one lake core is curiosity. The same anomaly turning up in separate basins, in a cave flowstone, and as a faint echo in coastal shelf mud, the pattern starts to look like behavior. Another principle: specificity. Natural processes are brilliant generalists. Volcanoes scatter weird glass. Wildfires darken soils and spike charcoal. Microbial blooms toy with carbon isotopes. But industrial life tends to bundle signals that nature rarely packages together. A synchronous carbon isotope excursion, paired with unusual ratios of rare metals. Think the rare earths used in electronics. Paired again with synthetic polymers or fluorinated compounds that biology doesn't build. Rocks keep receipts, one stratigrapher likes to say. You just have to know what charges never appear on a natural bill. We should also manage expectations about artifacts. Stone tools can last. Ceramics can last longer. Glass can last longer still, though it weathers. Metals? Most don't stand a chance near the surface unless sealed. Concrete can mineralize into something stone-like, but recognizability fades. The most durable technofossils may be weird minerals, phases that only form in blast furnaces or incinerators, now showing up as the planet's newest rocks. If a prior civilization ever invented its own suite of odd minerals, those might be the breadcrumbs. Grains with element ratios that don't belong with any known magmas, welded into ancient dumps, or buried by floods. Here's a quiet complication. Vaults preserve, but they also bias. Caves skew toward upland signals. Lakes overweight local watersheds. Bogs prefer cool, wet climates. Salt pans love deserts. Any global story assembled from vaults is stitched from partial views. That's not failure. That's fieldwork. The solution is breadth. More cores, more caves, more basins, more comparisons. Boring? Literally. Transformative? Also yes. You might wonder, have we ever pulled up something that feels too odd? Scientists sometimes report unassigned peaks, mystery compounds in mass spectrometers that don't match, modern libraries or stubborn particles in old sediments that resist easy classification. Most eventually find homes in the catalog. Some wait years. A few are filed as unresolved. The healthy posture is patient skepticism. Assume nature first. Keep the door ajar. As one geochemist put it, extraordinary claims don't need extraordinary belief. They need boring, repeatable lab work. The tenderness of this whole exercise is that our best hope for finding another us is to become better at reading ourselves. We are currently seeding the vaults. Lake cores are catching our fertilizers and microplastics. Cave stripes are logging our aerosols. Bogs are darkening with our soot. Salt basins are swallowing our dust. Future minds, human or not, will read those ledgers and infer a civilization. The question we're asking tonight flips the arrow of time. Could we do the same in reverse if someone long ago nudged the planet in ways that rhyme with our own? A final image to carry into the next chapter. Picture a lab bench at midnight. On it lie 3 slender cylinders of mud from different lakes, a polished slice of cave flowstone, and a vial of grains from a desert basin. Under the microscope, A technician sees the same tiny shard in each, a glassy, angular fleck with an element recipe nothing in the local geology explains. She checks the dates. The layers align. She checks another lake. It's there too. The shard isn't a statue or a script. It's a receipt. And it's the kind of small, stubborn clue that could shift a story. Nature is generous with patterns, a stratigrapher said. If you see the same odd chord in 3 different songs, start asking about the composer. If you're going to hunt for the echo of a vanished civilization, you have to make peace with a tricky truth. Nature is a brilliant impersonator. Volcanoes can fog the sky with strange gases. Meteorites can pepper the world with glassy beads. Microbes can swing the carbon cycle like a pendulum. Many of the industrial fingerprints we might expect to find in rock carbon spikes. Odd metals should also appear when the planet throws one of its own parties. So the question isn't just, is there a signal? It's, does this signal look like something only technology would do? As one geochemist likes to say, don't chase soloists, listen for the whole band. A classic example of a band is the dinosaur-ending asteroid. At the Cretaceous-Paleogene boundary, a razor-thin layer appears in rocks worldwide. It's rich in iridium, a metal more common in meteorites than Earth's crust, sprinkled with shocked quartz, grains scarred by extreme pressure, and filled with spherules tiny glass beads formed from rock vapor. Any one of these could be shrugged off as unusual. All 3 together, globally synchronous? That's a chorus you can't mistake. Definitions, quickly. Shocked quartz shows microscopic fractures that form only under colossal impacts. Spherules are droplets that cooled mid-air after an explosive melt. Bundle the clues and the cause resolves, like a face in a pointillist painting. Now compare that to a different kind of upheaval, the Paleocene-Eocene thermal maximum, about 56 million years ago. In a geologic blink, the planet warmed, oceans acidified. A big negative carbon isotope excursion shows up in sediments. Translation: the ratio of carbon-13 to carbon-12 shifts toward lighter carbon, as if a lot of CO or methane flooded the system at once. If you only looked at that ratio, you might whisper fossil fuels. But nature has several ways to pull this trick massive volcanism. Methane released from seafloor ice, clathrates, even huge peat and permafrost burns. The Petnam looks eerily like us in some ways, but there's no iridium, no synthetic molecules, no telltale fly ash spheres. It's a reminder that one instrument can play more than one melody. Another master of mimicry, the ocean itself. In the Cretaceous, ocean anoxic events painted seafloors with black shales, organic rich muds laid down when deep waters lost oxygen. These layers can be loaded with metals and sulfur compounds. They scream pollution to a modern eye, but they're powered by climate and circulation quirks, not factories. Warm seas stratify, nutrients spike, dead zones spread, and the chemistry writes a dark, heavy signature. A paleoceanographer once told me, the ocean doesn't need smokestacks to make a mess. It has weather. So what would make a signal feel less like a natural disguise and more like a confession? Specificity and bundling. Technology tends to package things that nature keeps apart. Think of spherical fly ash, particles microscopic glassy balls formed in high-temperature coal combustion. Under a microscope, they look like tiny moons, smooth and near-perfect. Winds loft them across continents. Snow and rain wash them into lakes and ice. We already find these modern beads turning up in sediments from the 1800s onward. If you ever found a tight, ancient horizon of the same distinctive spheres, paired with a sharp, global carbon isotope swing, and say, weird fluorinated organics, industrial compounds that biology doesn't build, that would be eyebrow-raising. Rocks keep receipts, a stratigrapher told me. You're looking for a purchase history that doesn't match any natural shop. Proxy is a useful word here. It means an indirect measure that stands in for something you can't sample directly. Pollen grains are a proxy for local vegetation. Oxygen isotopes in shells proxy ocean temperature. Charcoal counts proxy fire. None of them tell a full story alone, but together they can sketch a plot. For an industrial fingerprint, the proxies we'd want to see sing in harmony. Soot and fly ash spheres for combustion. A distinctive, rapid shift in carbon isotopes for added fossil carbon. A rise in certain metals used in electronics, nickel, rare earth elements, in ratios unlike volcanic ash. And traces of synthetic organics, long-chain polymers, or fluorinated compounds that don't appear in pre-industrial chemistry. That bundle, across multiple sites, lining up in age, is the whole band. False positives lurk everywhere. Volcanoes release mercury and CO. They scatter ash full of glass shards and crystals. Asteroid impacts forge spherules, and even carbon soot from wildfires they ignite. Microbes can produce odd hydrocarbons. How do you not get fooled? One way is shape and texture. Fly ash spheres are highly uniform and often hollow, or with internal bubbles from rapid cooling volcanic glass tends to be more jagged, with different chemistry. Another is time thickness. Industrial layers should appear almost instant compressed into millimeters compared to slower, smeared natural shifts. A third is chemical weirdness. Fluorinated compounds, the backbone of Teflon-like chemicals, and certain plastics have carbon-fluorine bonds that natural processes don't favor. Even when broken down, they can lead distinct fluorine spikes bound to organic fragments. Chirality, the handedness of molecules, can help too. Life strongly prefers left-handed amino acids. Many industrial syntheses create equal left and right, finding an ancient layer with a suite of complex organics that are racemic, even-handed, where biology would usually be skewed could nudge an interpretation away from purely natural origin. It wouldn't prove factories, but it would complicate the just microbes answer. Spatial patterns matter as well. Natural events have their own fingerprints in space. Volcanic ash thins with distance from its source and has a chemistry that matches a particular magma. An impact sprays a global but size-sorted rain of spherules. Industrial activity, by contrast, clusters along coasts and winds. You might see downwind plumes in lake cores, with strongest signals near former population belts and a gradient inland. If a 70-million-year-old lake in the interior of an ancient continent shows the same intense industrial cocktail as a coastal basin, you'd ask different questions than if only coasts lit up. There's a sobering limitation: time resolution. Many sediments compress centuries into a single millimeter. If an industrial phase lasted 200 years long for us, short for rocks, it might appear as a razor line. Separating subdecadal pulses in such a line is like trying to read footnotes on a postage stamp. That means our detective work often has to accept blur. We rarely get frames, a paleoclimatologist said. We get the movie, fast-forwarded. Another tool is minerals that only human heat tends to make. Industrial slags metal-rich glassy, lumps from smelting cool into odd mineral assemblages that magmas don't produce at the same compositions. Cement and concrete spawn calcium silicate hydrates and, over long burial, can recrystallize into unusual rock-like masses with telltale textures. If you found a lens of such material, reworked and buried, you might not read bridge or building, but the chemistry would sit uncomfortably outside nature's usual repertoire. And yet, even with all these tricks, humility is crucial. A single weird peak in a mass spectrometer can be contamination. A single sphere can be a natural concretion, a lump cemented by groundwater that happens to look manufactured. A single drop in sea can be a swamp burning on a hot summer, scaled up across a continent. The discipline that protects us from fooling ourselves is repetition. Different sites, different materials, same story. If the chords recur in caves, lakes, and ocean muds and the dates rhyme, you're listening to composition. Not coincidence, said a stratigrapher who spends more time than most staring at bands of mud. What might a smoking gun-ish scene look like? Imagine a narrow clay horizon and multiple lake beds, all dated to the same brief interval. Under the microscope, abundant fly ash spheres, not volcanic shards. In the chemistry, a sudden steep negative carbon isotope excursion, accompanied by elevated nitrates, think fertilizers, and a spike in fluorine bound to organics. Mixed in, a peculiar pattern of rare earth elements, neodymium, dysprosium, at ratios that don't match regional rock. In one cave, a matching stripe appears in dripstone from the same years. In an ocean core offshore, a thin layer shows similar signals, diluted but present. That is not a pyramid. It's a receipt, and you take it seriously. For balance, here's a scene we already know is natural, but theatrically convincing. A massive basaltic eruption, the kind that builds flood basalts, roars for tens of thousands of years. CO rises. Mercury spikes. Ash rains over half a continent. Black shales accumulate where seas go sluggish and anoxic. In the record, this looks like global stress and widespread pollution. It is just not ours. The bundle here is different. Volcanic glass chemistry, plume-ward metal gradients, the slow burn thickness of layers. The band plays at different tempo. In the end, this is less a treasure hunt than a literacy lesson. We're teaching ourselves to read a language written in mud and calcite, in spheres and stripes, in ratios and residues. The test isn't whether we can prove someone came before us. It's whether we can tell a natural crescendo from a technological chord without wishful hearing. The good news is we're getting practice, because our own score is being written right now, an Anthropocene line thin enough to slice, loud enough to hear for a long time. Nature is generous with patterns, that same geologist said softly. If intelligence happened twice, it wouldn't need to carve statues. It would have left a pattern that doesn't belong. If Block 6 was about not being fooled by nature's disguises, this one is about where to look when you want the truth anyway. Ask any field scientist where the past hides, and you'll hear a similar answer in different words. It hides in slow places. Places that don't churn much, don't erode fast, don't get dragged down a tectonic throat and melted. Find the slow shelves, a stratigrapher once told me, tapping his core samples like old books. The past files itself where time moves like honey. Start with the seafloor specifically, the quiet basins far from shore where fine particles rain down year after year. Imagine a snow globe that never gets shaken. Tiny shells, dust, soot, and chemical fallout settle into whisper-thin layers. Over millions of years, those layers turn to rock, and that rock keeps a running tally of what the world was doing above. In some basins, the water near the bottom runs short on oxygen, which sounds ominous, but is great for preservation, because scavengers and burrowing creatures don't stir the sediment. That stillness lets delicate clues survive. Microscopic glassy spheres from high-temperature combustion, odd metal ratios, even the ghosts of synthetic molecules locked into clays and organics. The ocean destroys many things, but its deepest, calmest rooms behave like archives. Lakes write even neater diaries when conditions are right. In a few of them, seasonal layering is so crisp you can count the years like tree rings. Geologists call those annual bands varves, from a Swedish word for turn or layer. A bright layer might mean a spring flood brought in silt. A dark one might be the quiet of winter settling. If something abrupt happened, a pulse of fly ash from distant smokestacks, a spike of nitrates from fertilizer washed off fields, a dusting of unusual metals, it can appear as a razor-thin stripe you can follow with a microscope. One paleolimnologist joked that lakes are nosy neighbors with perfect memories, because they sit downwind of continents and eavesdrop on whatever the air brings. The walls of caves keep another kind of log. When mineral-rich water drips from a cave ceiling, it leaves behind a film that slowly grows into a stalagmite. Those dripstone towers, collectively called speleothems, trap traces of whatever was in the water and air above. Layer by layer, they record rainfall chemistry, trace metals, even changes in the surrounding soil. A stalagmite doesn't look like a scientific instrument, but sliced open, it reveals bands that can be dated and sampled. Caves are time capsule factories, a geochemist told me. Each drop is a data point. If an industrial plume passed overhead for a few centuries long ago, a stalagmite might quietly have inhaled it. On land, peat bogs, loess plains, and desert varnish add quieter voices to the chorus. Peat, the half-decayed plant matter that builds up and cool, waterlogged places, tends to hoard whatever falls onto it. Pollen, ash, metals, and the byproducts of combustion. Loess is wind-blown silt that collects in thick blankets downwind of dusty regions. It layers up like a stack of pale pancakes and can preserve subtle dust chemistry from faraway sources. Desert varnish, the thin, dark patina that forms on sun-baked rocks, is a slow-motion paint job built by microbes and minerals, and it can trap airborne metals in its glaze over tens of thousands of years. These aren't million-year ledgers on their own, but they bridge gaps and cross-check stories told by lakes and seas. Ice is the least ancient, but the most precise. In polar cores, we can often read year by year for hundreds of thousands of years, sometimes more in special sites. Air bubbles preserve past atmospheres. Thin bands capture ash from eruptions and dust from deserts. Fallout from human nuclear tests in the mid-20th century sits in a clean, datable stripe. Ice won't tell you what happened 50 million years ago, but it's our yardstick for what an industrial signature looks like in a perfect modern archive. Train your eye on the Anthropocene layer in ice, then go hunting for family resemblances in older, Messier materials. Finding the right shelf is only half the game. You still have to know where that shelf was on the ancient map. Continents wander, seas appear and vanish, wind belts shift. Paleogeography, the reconstruction of old Earth maps, tells you how to cast your net. If you think an industrial plume existed on a long-vanished coastline, you don't drill at today's beach. You follow the rocks that formed along that ancient shore and sample downwind basins that existed at the same time. It's cartography meets detective work. One mapper grinned and called it CSI, Gondwana. Then there's the tricky business of dating. For the recent past, we use radiocarbon, a steady decay of carbon-14 in once living things, to pin years to layers. For older records, other clocks take over. Uranium-thorium dating for cave formations. Argon-argon for volcanic ash. Uranium lead in zircon crystals. Magnetostratigraphy helps too. As lava cools or sediments settle, iron-bearing minerals line up with Earth's magnetic field. Because that field has flipped many times, those flips create a barcode pattern in rock. Match the bars and you match the time. None of these methods are exotic to geologists. That's the point. A credible search for deep-time technosignatures rides on the same rails we already trust. One practical way forward is to take the world's core libraries, tens of thousands of tubes of mud and rock in freezers and warehouses, and ask new questions of them with new tools. We can scan for spherical fly ash, for spikes of fluorine bound to organic fragments that hint at fluorinated compounds, for unusual rare earth patterns, more typical of refining than of volcanic glass. We can run blind tests where the instruments learn the chemical fingerprint of the last 2 centuries, and then look for miniature versions of that fingerprint in older layers, knowing they'll be faint and scrambled. It's like teaching a dog a new scent, then letting it sniff every page in the archive. Contamination is the villain in any story like this. Modern plastics flake from clothing. Metal tools shed particles. Even breath can alter a sensitive chemical measurement. So the work looks a lot like medicine. Clean rooms, blank controls, repeat runs in independent labs. The simplest way to discover an ancient plastic layer is to wear a fleece jacket while sampling. One lab manager said with a pained smile, "If a signal survives those defenses, it deserves attention. If it disappears, it wasn't the rock talking." Patterns matter more than trophies. A single quirky sphere is an anecdote. A cluster of identical spheres that appear in the same narrow slice of many lakes, with the same companion chemistry, a sharp carbon isotope drop, elevated nitrates, a whisper of fluorinated organics, that's a pattern. You'd want the same story in a stalagmite, in an offshore marine layer, in dust locked into soils. You'd want the timing to line up across continents once you translate each archive into the same calendar. If the melody shows up in different instruments, a paleoclimatologist told me, it's probably the song, not the static. There's a second map to draw while you hunt, where not to waste time. Places battered by glaciers, jumbled by landslides, or cooked by igneous intrusions scramble the record. Active mountain belts lift and erode too fast. River floodplains edit savagely. A smart search aims for geologic backwaters, old, stable cratons with long-lived lake basins, continental margins that subsided gently, deep basins that stayed starved of oxygen. The planet is noisy. You're looking for its quiet corners. There's a human side to the hunt, too. Many of the best sites sit within protected lands or sacred landscapes. Extracting a beautiful stalagmite is not just a technical decision, it's an ethical one. The same is true offshore. Coring the seafloor disturbs it. The right approach is surgical small, justified, and guided by local communities. We are guests in Earth's archive, an archaeologist reminded me. We sign in, we read carefully, we put the book back. A funny twist to all of this is that our own brief era is the training set. If future beings ever try to recognize civilization in a layer, they'll calibrate on us. The carbon swing, the fallout pulse, the microplastic sheen, the global synchrony. We get to do that calibration now and feed it backward into deep time. Maybe nothing will rhyme. Or maybe, in some thin, stubborn horizon in rocks older than any city, the chorus will sound familiar. None of this requires believing an earlier civilization existed. It just asks us to look with the best tools we have, in the best places to preserve a whisper. If nothing shows up, we sharpen our understanding of natural extremes. If something ambiguous turns up, we test it to within an inch of its life. If something compelling turns up in many archives at once, well, then we have a conversation. The past won't hand you a flag, the stratigrapher said, sealing another core. If there was a message, it's in the margins. And that's the practical plan. Go to the slow shelves. Date the pages precisely. Read with clean hands. Compare many chapters. Trust patterns over pretty curiosities. Above all, accept that deep time speaks softly. If intelligence happened twice, the evidence will look less like a monument and more like a motif. If Earth is a busy house that keeps redecorating, the moon is the attic no one ever cleans. No rain, no rivers, no plate tectonics, barely a whisper of an atmosphere. What lands there tends to stay scuffed, sun-bleached, and slowly buried by dust, but not dragged into the mantle or washed out to sea. That makes the moon, and a few other airless worlds, quietly valuable to a question like ours. If something intelligent changed this planet long before we arrived, some of the shrapnel of that story might have flown off-world and come to rest where time moves very, very slowly. Here's the simple physics. When a big asteroid hits Earth, it blasts rock into space. Some of those fragments are ejected fast enough to escape gravity, loop around the sun, and over thousands of years fall back onto other surfaces. The Moon, Mars, even small asteroids. We've seen the reverse happen. Martian rocks have landed in Antarctica. We've picked them up and studied them. There's no rule that says the traffic only goes one way. Geologists call these traveling chips ejecta, and when they take up residence on another world, They become a kind of accidental courier service for old stories. The lunar surface is especially good at receiving mail. Its top layer, a powdery soil called regolith, think ultrafine, shattered rock, is created by constant micrometeorite impacts. Those tiny its also garden the surface, slowly mixing and burying whatever sits there. Its destructive radiation and micrometeorites chew at exposed materials. But it's also protective once something gets buried a few centimeters down. On the moon, 6 inches can be the difference between a decade and 1,000,000 years. As one lunar geochemist likes to say, what could survive that journey? Not paper or wood. Sunlight and radiation would erase those in short order. But minerals, ceramics, glasses, certain alloys, and some chemical residues can be stubborn. Imagine for a moment an ancient industrial process on Earth that made unusual glass beads or ceramic microspheres. Impact ejection could loft a handful into space. If even a few landed on the moon and were quickly dusted over, they might persist as tiny curios in the soil out of place in composition or shape, waiting in the attic. Before this begins to sound like treasure hunting for trinkets, it's worth stressing a principle from earlier. Patterns matter more than trophies. A single odd sphere proves nothing. A layer containing many, clustered with a telltale chemistry, is different. On the moon, that would mean sampling regolith at depth and date, then asking, does this horizon contain shapes and compounds that don't match known lunar processes or ordinary Earth rocks? And do we see the same thing at widely separated sites, implying a planet-wide Earth source rather than a local lunar quirk? There are also chemical postmarks to look for. The moon's soil contains tiny glass spherules formed by impacts, each a melt droplet frozen in midair. Their composition fingerprints the rocks they came from. If a batch of spherules carried an unusual blend of trace elements, say, a rare earth pattern more typical of ore refining than of natural basalt, that would raise eyebrows. Likewise for stable isotope ratios, the natural mix of light and heavy versions of elements. Industrial processes sometimes fractionate isotopes in distinctive ways. Those subtleties can survive even when the original object does not. Mars offers a different kind of attic, not as pristine as the moon, but with layered deposits that act like shelves. In its polar regions and ancient lake beds, wind-laid and water-laid strata preserve dust and chemistry over long timescales. Mars does have weather, so it edits the record, but it lacks subduction and active plate tectonics. A deeply buried horizon could keep a quiet secret for millions of years. If Earth once shed debris during a colossal impact, some of it likely rained on Mars. The chance of anything recognizable is slim, but slim and impossible are not the same. Asteroids are the deep freezers of the solar system. Many are fragments of ancient, undifferentiated rock that have spent eons in cold storage. A few near-Earth asteroids probably carry tiny amounts of foreign material mixed into their regolith, swept up during flybys. If Earth ejecta ever dusted them, it's conceivable that microscopic remnants, exotic alloys, odd glosses, and unusual ceramic shard could be trapped there, shielded from weather by the vacuum of space. Skeptical voices belong in this room. Radiation on airless bodies is harsh. Polymers and many organics will not last. Micrometeorites are sandblasters. And even if a piece of Earth flew out, landed, and survived, finding it is a needle-in-the-sky problem. You're asking a small rover to find a pepper flake in a desert made of pepper. A mission engineer joked, "Fair, but we don't need a single dramatic artifact. We need repeatable signal statistical weirdness that persists across samples and sites." So what would a cautious, useful search look like? First, we'd piggyback on missions already planned. Sample return projects bringing material home from the moon, Mars, and asteroids are the gold standard because they let many labs interrogate the same grains with the cleanest techniques. We'd design a tiny technosignature kit, protocols and instruments tuned for out-of-place chemistry. Not new hardware necessarily, just new targets for the mass spectrometers and microscopes we already fly. Second, we'd use Earth as our key. Train lab analyzes on modern industrial signatures how fly ash spheres look, how certain fluorinated compounds behave when they bind to clays, how smelting slag differs from natural glass, and then ask the lunar and Martian samples if they've seen anything that rhymes. We can also make fake meteorites in the lab, bake mixtures of soils, metals, and synthetic compounds under radiation and vacuum to see what survives a million-year equivalent of punishment. That gives us templates, a menu of possible survivors to compare against real samples. Third, we'd map time. The upper few centimeters of lunar regolith represent thousands to millions of years of stirred-up history. Deeper cores, especially in permanently shadowed regions near the poles, could hold older, gentler pages. If a strange layer shows up at one depth in one core, we check the same depth in cores from other sites. If it's global and time-locked, the conversation changes. There's one more quiet archive off-world that rarely gets mentioned: the far side of the moon, where radio silence reigns. No modern broadcasts reach there directly. It is the quietest radio sky in our neighborhood. While that helps radio telescopes, the regolith itself might also have trapped traces of ancient electromagnetic activity in the form of fused grains or peculiar charge tracks. For example, if a truly massive planet-wide burst of radio noise ever occurred, that's speculative, and voices of caution would insist, rightly, on natural explanations first. But look where the noise isn't is a good general rule. Ethics again, even here. Cores and samples are finite. Every gram of returned soil is fought over by brilliant, careful teams. Folding a technosignature test into that workflow must add value, not distract. The goal isn't to hijack missions with a flashy quest. It's to squeeze extra meaning from the precious material we already gather. As one mission lead put it, every grain is a library. Be a good reader. If the attic is empty, no odd spheres, no chemical echoes, no isotope quirks, that's still an answer. It tells us that if intelligence flared on Earth long before us, it was either too gentle, too brief, or too different to leave a durable off-world trace. If, however, a faint motif repeats an anomalous glass chemistry at multiple lunar sites, or a peculiar rare Earth pattern in Martian dust from the same window of time, then we've earned the right to look harder, with better tools and more targeted samples. And even if we never find a whisper of anyone else, this off-world reading teaches us something humbling about ourselves. Our own material, already sprinkled across the moon by a handful of missions and a cloud of microscopic debris, is becoming part of that attic. The boot prints, the chips of paint, the flecks of metal. They are a postcard to the future from a species that briefly learned to climb out of its cradle. If someone comes looking one day, that might be the first line they read. Stone forgets and the ocean erases, but life gossips. Forests, microbes, shells, bones, they all react to what happens around them. The question is whether any of that reaction could outlast the storytellers. If something intelligent once stirred this planet long before us, might the biosphere itself have kept a faint, testable memory? Start with the obvious recorder DNA, and the first hard limit: DNA is not a granite monument. It's a fragile notebook. In the best freezers nature can offer, permafrost, caves, dried deserts, fragments can hang on for hundreds of thousands of years, maybe brushing 1 million under exceptional conditions. But the moment you ask for 10 million years, let alone 100, the ink is gone. Proteins last longer than DNA in some settings. Pigments in fossil feathers and eggshells can persist as ghostly chemical outlines. Lipids, fat-like molecules, and certain cell wall bits from microbes can fossilize as biomarkers. Still, anything that would let us read an ancient genome the way we'd read a book is off the table. That means direct genetic proof of an engineered past civilization is unlikely. We're left with indirect traces, what biologists call signatures of selection and environmental change. One such signature is domestication. Domestication leaves a very specific set of scars on anatomy and population genetics. Rapid growth, juvenile features retained into adulthood, altered skull shapes, reduced defensive structures, and in plants, seeds that cling to the stalk rather than shattering in the wind. Think of modern broiler chickens, outsized, fast-growing, with bones and breast muscles that don't appear in wild relatives. If some distant era showed the sudden rise and global spread of animal morphologies tuned for human-like needs, fatter, tamer, oddly proportioned, in multiple species at once, that would be eyebrow-raising. In plants, a pollen record abruptly dominated by just a handful of heavy-seeding grasses, appearing across continents in the same narrow slice of time, would whisper fields rather than wilderness. The trouble is that nature can sometimes produce similar patterns. After mass extinctions, a few generalist species often bloom and dominate. Floodplains can favor one hardy grass for a while. To argue domestication from bones and pollen alone, you'd need global synchronicity, dramatic speed, and a package of traits that together look less like recovery and more like management. Microbes are even better tattletales. They evolve quickly and adapt to new chemicals with ease. When we release novel compounds, detergents, solvents, pesticides, microbial communities reshuffle. New enzymes emerge, old ones get repurposed, and breakdown products accumulate. A famous modern example is pitase, an enzyme that helps some bacteria nibble at plastic bottles. It didn't come from nowhere. It's a tweak of existing enzymes for natural polyesters. But its rapid rise tracks a distinctly human pollutant. If a deep-time sediment layer showed a worldwide pulse of exotic, organic residues alongside a shift in microbial biomarkers, say, a bloom of compounds associated with the degradation of long-chain, fluorinated molecules, natural explanations would have to work hard. Volcanoes and hydrothermal vents make plenty of weird chemistry, but some modern industrial molecules sit far outside nature's usual recipe book. The catch is durability. Many synthetic organics break down or get recycled by microbes with enough time. So again, you'd want patterns across sites, not single curios, and you'd lean on compounds known to resist decay and bind to minerals. Shells and skeletons act like time capsule tape recorders. As organisms build carbonate, think shells, corals, some plankton. They incorporate trace amounts of metals and different versions of elements called isotopes. Those tiny inclusions reflect the water they lived in, its temperature, acidity, and dissolved chemistry. Massive fertilizer use today, for example, is shifting the nitrogen cycle. In sediments and shells, that shows up as changes in nitrogen isotopes. Coal burning alters sulfur signatures. Industry moves lead and rare metals in ways volcanoes don't. If an ancient thin horizon in marine limestone showed a tight, global spike in industrially suggestive metals, lead, tin, arsenic, in ratios typical of smelting wastes, or rare earth patterns that look like ore processing rather than normal basalt weathering, paired with isotopic fingerprints that shout rapid planetary disturbance, it would be hard to wave away. You'd still test volcanic and asteroid hypotheses, but a layered bundle of clues, all pointing the same direction, starts to look less like geology and more like agency. Another angle is ecological rearrangements that don't fit the usual playbook. Agriculture simplifies landscapes. It compresses biodiversity into rows and concentrates nutrients in soils. Over time, you get compacted ground, lost topsoil, altered fire regimes, and tree lines pushed back. In the deep archive, that might appear as a pattern of charcoal spikes followed by long runs of monotonous pollen-fused species. High counts, then a sudden rise in erosion markers as fields wash into lakes. We do see charcoal and pollen swings tied to climate and lightning. We do see erosion after natural vegetation shifts. But to argue cultivation, you'd want region-wide synchronization across climates that shouldn't have moved in lockstep. And you'd want the agricultural signature to persist across centuries in that layer, not just a season's burn. What about the most tempting idea of all? Engineered code hiding in the tree of life watermark sequences, unnatural codon patterns, amino acids from outside biology's standard toolkit. Here the physics of decay shuts the door almost completely. DNA that old is gone. Proteins race-mise, their handedness flips and crumble. Even if a civilization had encoded a message in bacteria, hoping spores would ferry it forward, time would erase the text. The more robust possibility isn't a literal message, but a forced change genome-wide pattern that pushed a whole clade, a branch on the tree of life, in an unnatural direction quickly. We sometimes see natural selective sweeps in which a beneficial mutation races through a population. In principle, synchronized sweeps across continents in multiple species at once could flag coordinated selection. In practice, detecting that millions of years later, without DNA, is like trying to reconstruct a song from the way a crowd once danced. Here's a humbling cautionary tale from real science. For years, certain fossil molecules called sterins were held up as evidence that complex eukaryotic life had already diversified billions of years ago. Later work showed that many of those signals were likely contamination from younger oils. Same rocks, same labs, different conclusion once cleaner methods arrived. The lesson isn't, don't trust biomarkers. It's treat extraordinary readings with extraordinary care. Or, as Carl Sagan put it, extraordinary claims require extraordinary evidence. There are, however, two biological technosignatures that future geologists will have no trouble seeing from us, and they're useful as thought experiments. One is the sudden, global appearance of a single domestic animal at staggering abundance, the broiler chicken. Its bones are everywhere, massively different from wild jungle fowl, with butchery marks and growth lines that speak of industrial life. The other is the widespread presence of plastiglomerate, a literal rock formed when melted plastic fuses with sand, shell, and lava fragments. These are durable, unambiguous markers of a technological biosphere. When we ask what to look for in deep time, we can ask a simpler version. Do we see anything analogous? A single animal skeleton type exploding worldwide with domestication traits? A novel composite rock formed by heat binding together natural grains and a stubborn synthetic? So far, no. So what would a careful biological search look like? We'd triage a few windows of special interest then, global layers where climate and life shifted unusually fast, and throw a multidisciplinary toolkit at them. Pollen and spore counts to test for agricultural monotony. Trace metal and isotope profiles in shells and fish teeth to sort industrial-like chemistry from volcanic. Molecular fossils of microbes to see if degraders of exotic organics bloomed and persisted, and where ancient DNA barely survives late Pleistocene layers at best, we'd still scan for odd codon biases or watermark-like repeats, knowing we're skirting the very edge of possibility. Just as important, we'd build null models of what volcanoes, impacts, and ocean anoxia usually look like in these same measurements, so we don't jump at every weird squiggle. If the biosphere is quiet no domestication morphologies, no agricultural pollen plateaus, no industrial metal patterns, that's not a defeat. It narrows the space of plausible stories. It says that if intelligence flared before us, it was either brief, local, light-handed, or very unlike us in its relationship to matter and food. If a small chorus of weak signals hums in tune across independent measures, we keep listening patiently, skeptically, with the humility this kind of question deserves. Life does gossip, but across deep time it whispers, and the page it writes on is always being torn and used again. If there was an older conversation, we may never hear more than a few syllables. That's all right. A few syllables, repeated in the right places, would still be enough to change the way we think about our own voice. If life whispers, rock keeps receipts. Every lake bed, river delta, cave floor, and quiet ocean basin is a ledger, page after page of dust, shells, ash, and ions settling out of water and air. The trick is learning which lines on the page came from volcanoes and meteorites, and which, in principle, could only have come from factories, furnaces, and power plants. Geologists have a blunt name for that kind of hunt: geochemical forensics. Let's start with a word you already know, but maybe haven't met properly: isotope. Think of an element like carbon as a family name. Members of the family share the same chemistry, but some siblings are heavier because they carry extra neutrons in the nucleus. Carbon-12 is the light one, carbon-13 a touch heavier. Plants prefer the light sibling when they photosynthesize, so fossil fuels ancient plant matter carry that lighter signature. When an industrial civilization burns a lot of that carbon in a hurry, the atmosphere and oceans record the shift, a planet-wide nudge toward the lighter isotope. That shift then seeps into anything that grows a shell or lays down carbonate rock. Years later, you can take a tiny drill to an ancient clam or a speck of limestone and read the ratio like a time stamp. Natural events can make similar marks. Rapid warming episodes in deep time show big carbon isotope swings. Massive volcanoes can rearrange the atmosphere for ages. Nature writes in bold strokes, as one stratigrapher likes to say. So a single isotope curve isn't enough to argue for industry. You need a bundle of oddities that rise and fall together, fast and across the whole globe. One of the most distinctive oddities from our own era looks like soot turned into beads. When coal burns in modern power plants, it can produce tiny glassy spheres called fly ash spherules. A spherule is exactly what it sounds like: a microscopic, almost perfectly round grain formed when droplets of molten material cool in air. You also get spherules from meteor impacts. Those often carry shocked minerals that have been squeezed by insane pressures, and from volcanoes. But fly ash spheres carry a different chemistry. They're flecked with a particular mix of trace metals and often show textures that betray their birth in a controlled, oxidizing furnace rather than an erupting crater. If you find a sudden, thin layer of those industrial-style beads on multiple continents, and the ages line up, you're not looking at a thunderstorm. Heavy metals tell their own stories. Lead is a classic. For decades, people added tetrethyl lead to gasoline. The result was a global dusting of lead that shows up in ice cores and sediments with a very specific pattern of lead isotopes. The lead family includes several stable versions that occur in different ratios depending on the ore and the processing. Smelting and fuel use also move cadmium, zinc, and mercury into places they don't usually concentrate on their own. One anomaly is a curiosity. 5 coherent anomalies is a pattern. A geochemist once told me, in rock, that means you're looking for a suite. Lead rising with mercury, with vanadium and nickel, common in certain oils, with a downshift in carbon-13, and with a surge of black carbon soot particles. Volcanoes can make some of that stew. Factories make the whole batch at once. Then there are the metals with glamorous names but unglamorous uses. Rare earth elements, Res, like neodymium and dysprosium. They're crucial for magnets, screens, and batteries. Industrial processing of Res leaves a fingerprint and uneven barcode of element ratios and odd isotopes. It doesn't look like the smooth background of weathered rock. If a thin layer in widely separated basins suddenly shows the same quirky barcode, you have to ask why. Industrial chemistry leaves more than metals. It invents minerals. Break concrete and asphalt into chips, bury them, and you're halfway to a rock geologist's now joke name urbanite. Melt plastic on a beach, and it can glue sand and shell fragments into plastiglomerate, literal plastic stone. At high temperature, you even get glassy crusts that look like the greenish trinitite formed in nuclear test blasts. None of these are common in nature. They are clumsy, unmistakable mashups of human habit and geology's patience. Will plastiglomerate last for millions of years? Pieces, probably, especially if they're quickly buried in quiet lake muds. Even when the plastic itself breaks down, it can leave behind odd, carbon-rich residues and the mineral shapes of its once melted bonds. Speaking of nuclear, radionuclides are the closest thing we have to a geological neon sign that reads, "Technology was here." A radionuclide is an unstable isotope that decays over time. Above-ground nuclear tests scattered isotopes, like cesium-137 and plutonium-239 around the world. They've been measured in ice, soils, and sediments as a spiky, global time marker. The catch is half-life, a time for half of a given amount to decay. Cesium-137 fades on the scale of centuries. Plutonium-239 lingers for tens of thousands of years. Millions of years out, most of those signatures will be faint, but not necessarily gone, especially if they're locked in minerals or entombed in anoxic, oxygen-poor muds. And if, in some far layer, we found a plutonium isotope that doesn't occur naturally at all, in measurable quantities appearing worldwide in a razor-thin band, we would be looking at a very weird day in Earth's history. Now for the skeptic's toolkit, because you need it here. Volcanoes can spew metal-rich ash half a planet away. Huge lava provinces can stoke CO for 1,000,000 years. Meteor strikes can rain spherules and iridium. They can make shocked quartz and glass. Wildfires fill the air with soot. Oceans can burp methane. Each of those, on its own, can mimic a piece of the industrial puzzle. But the combinations matter. Volcanic ash layers typically contain volcanic glass and crystals with mineralogy that screams magma, not furnace. Impact layers come with shocked minerals, and often a spike of extraterrestrial metals like iridium. Methane releases shift carbon isotopes, but don't make fly ash spheres in coal plant ratios or scatter man-made alloys. Agriculture can explain long runs of monotonous pollen. It can't explain a sudden global dusting of alloyed metal flakes. A famous natural yardstick is the thin band at the end of the Cretaceous, the day the dinosaurs' luck ran out. It's a crisp layer in many places. Iridium spike, shocked quartz, glass spherules, soot from world-spanning fires. We can tie those signals to a single cause, a rock from space. The lesson isn't look for dinosaur killer drama. It's that some short-lived, global events write sharp. Layered signatures we can still read 66 million years later. If an industrial civilization briefly wrapped the planet in its chemistry, it should leave a comparably sharp, if different, layer. So where do you look for such a layer? Quiet places, lakes that lay down paper-thin varves, annual layers, like tree rings. Oxygen-poor ocean basins where carcasses don't rot and mud stacks up undisturbed. Stalagmites in caves that grow millimeter by millimeter and trap airborne dust in annual bands. Peat bogs that sip the atmosphere and keep its metals. Desert playas that turn stormwater into film-thin sheets of sediment. You target windows where nature's pen never lifted. What would count as a persuasive package? Picture this in a core sample. A centimeter or two were black carbon spikes. Carbon to 13 drops fast. Lead, zinc, vanadium, and mercury surge together in industrial ratios. Fly ash spherules abound. A faint trace of synthetic-like organics clings to the clay. And the same pattern appears in lakes on 3 continents in the same geologic moment. At an odd rare earth barcode and a dusting of long-lived radionuclides. And suddenly, volcano has to wrestle with a lot of coincidences. As one field geologist quipped, rocks don't believe in coincidences. Of course, time is a vandal. Ocean crust is recycled. Mountains uplift and crumble. Even quiet lakes fill or drain. That means most of the planet's surface area won't preserve a clean record across tens of millions of years. The practical response isn't despair, it's statistics. You don't need every page. You need enough good pages from enough quiet libraries to see whether a strange sentence appears more than once. There's one more honesty check. If we ran our own story forward 1,000,000 years, much of our built world would be gone. But a thin planetary rash of technofossils plastaglomerate pebbles, concrete dusts turn to new minerals, fly ash beads, alloy flakes, radionuclide ghosts would still be findable in the right vaults. That becomes our template. We ask of any ancient horizon, does it look even a little like us? So far, where we've looked carefully, the answer is no. That no doesn't slam the door, but it narrows the gap, and it tells us what to measure next. We read the planet the way a doctor reads a chart, another stratigrapher told me. You don't diagnose from one number. In rock, as in medicine, it's the vital signs together that matter: pulse, temperature, pressure, chemistry, all changing at once, all pointing the same way. If an earlier pulse ran through Earth's veins, the right cores from the right quiet places might still catch the echo. If Earth is a self-erasing chalkboard, the rest of the solar system is a set of filing cabinets that rarely get cleaned. That's the quiet twist in our question. If anything intelligent ever tinkered with this neighborhood, us or not us, some of the most durable evidence may not be on Earth at all. The places to check aren't the lush or the lively. They're the airless, the cold, and the still. Start with a simple idea. Preservation loves boredom. The moon is boring in exactly the way a museum curator would adore. No rain, no rivers, no plate tectonics. Just sunlight, darkness, micrometeor dust, and time. Its surface is covered with regolith pulverized rock and glass beads produced by endless tiny impacts. If you want a planet that keeps secrets, go to the moon, a lunar geologist once said. It's true figuratively and almost literally. The Apollo landing sites are still there, down to the trails of the astronauts' boots. That's after only half a century. Now scale that forward. In the lunar environment, a metal object can sit for millions of years and only slowly pit under space weathering, the sandblasting by micrometeorites and solar wind. Paint fades, plastics crack, but geometry straight edges, drill holes, right angles can hang on a very long time, especially if it gets buried by a dustfall and sealed. That makes the moon a kind of attic for technofossils, the durable leftovers of technology. A technofossil is any manufactured thing that can survive to become part of the geologic record. Glassy slag, strange alloys, fused sand. Think beach sand welded into rock by heat. Even concrete like breccias produced by construction or high-energy experiments. On Earth, those traces get recycled. On the moon, they accumulate. If an earlier civilization ever left artifacts, their tools, beacons, mining tailings, we wouldn't expect shiny spacecraft waiting for a postcard shot. We'd expect weathered debris fields, unusual glass, geometric scrap, or disturbingly straight trenches in the dust where natural processes tend to scribble in curves. Regolith is the right word here because it also behaves like a tape recorder. Layers of dust settle, impacts churn, and over time you get a stratigraphy, stacked layers, that captures events. A brief episode of intense activity, say, repeated landings at the same patch of ground, or the heat bloom from a reactor could sinter, fuse the upper centimeters of soil into a crust with odd glass chemistry. Drill a core through that, and you might find a wafer-thin horizon with melted grains, vaporized metal flecks, and isotopes in ratios that don't match meteor impacts or volcanic glass. The moon has old volcanics, but nothing recent. That's how you'd read a lunar page for technology, by chemistry, texture, and geometry acting in chorus. Mars is Messier, but generous in a different way. It once had rivers and lakes. It still has deserts and cold. Wind sculpts, frost heaves, but Mars lacks Earth's grand eraser plate tectonics, so landscapes can persist for millions of years. The planet's dust storms are famous, yet much of the surface is a long-exposed rock garden. If someone altered a Martian valley quarried, a cliff, carved a roadbed, built berms for wind protection, erosion would begin softening the edges immediately. But the underlying pattern could linger as subtle terraces, unusually straight talus, rockfall lines, or unnatural distributions of boulders. We'd never trust shape alone. Nature makes hexagons, spirals, and perfect cones with cheerful ease. But shape plus context plus chemistry is persuasive. Spectroscopy, the art of reading composition from light in flag industrial minerals, glass with odd oxidation states, or cements that look less like basaltic weathering and more like binders cooked at precise temperatures. Mars also keeps airy time capsules in sedimentary rocks. Layered deposits in ancient lakebeds are like books whose pages are thin as playing cards. A few millimeters can represent a year, a few centimeters an era. If a brief wave of industry dumped metals into Martian water or dusted the atmosphere with combustion byproducts, those layers could trap a chemical blip. The blip might be a spike of elements used as catalysts, an unusual suite of rare Earth elements, the Rhees behind magnets and screens, or even microglobules of glassy ash, similar to fly ash from furnaces. None of those would prove intelligence by themselves. Volcanoes and impacts can copy parts of the recipe, but the full recipe is the tell. Tightly timed, globally coherent, chemically odd. And then there are small worlds with big memories. Asteroids are leftovers from planet building, chunks of metal and rock. It never became a world. They don't erode in the rainy sense. They just sit in the sun and get peppered. If you pull up a high-resolution image of a rubble pile asteroid, you see boulders, pits, and the random logic of gravity doing its slow work. That makes unnatural patterns, repetition, uniform spacing, long shallow cuts stand out if they exist. Mining, in particular, would leave bias. Natural craters have a certain size distribution, many small, few big, and depth profile. Systematic excavation prefers a target, say, nickel-iron nodules, and removes material in a way gravity alone wouldn't. A field of similarly sized, similarly shallow pits in a high-grade metal region, paired with tailings, waste rock, dumped downslope, and a dusting of alloy flakes, would look suspicious in a way a geologist could test. Even without a shovel, light can help. Reflectance spectra reveal surface composition. If an asteroid's skin is inexplicably depleted in the very metals, its interior should supply, or enriched in weird alloy grains processing, not weather, becomes a candidate explanation. One subtle place to look is the Lagrange points regions where gravity balances like a saddle and objects can loiter. The Earth-Moon and Sun-Earth systems have such points. They're not perfectly stable, but they're sticky. In the far future, artificial debris placed there could drift for ages. A deep survey might find fragments with unusual albedo, reflectivity, and spectral fingerprints too smooth, too uniform, too alloy-like to be natural fragments. As one orbital dynamicist put it, nature sprays. Engineers stack. Orbit itself can be an archive. Low Earth orbits decay quickly because the thin upper air drags satellites down. But far higher orbits, geosynchronous graveyard rings, highly elliptical paths, solar orbits well away from Venus and Earth, can be stable on timescales that embarrass our attention spans. Space debris won't stay pristine. It collides, it fragments, it darkens, but a long-lived cloud of fragments with tight, quantized inclinations, shared tilt angles is an engineer's calling card. The hard part is observational. Those pieces are tiny and dark. The signature may be statistical rather than photogenic. A pattern in radar glints that says design, not chance. What about comets? They're dirty snowballs on long loops through the deep freeze. Not ideal for building, but excellent for preserving volatiles, frozen gases, and organics. Technology interacting with comets would likely be in the form of redirected paths or harvested ices. That leaves astrometry precise orbit tracking as a weirdly philosophical technosignature. If a family of comets shows past orbital tweaks that don't match known gravitational resonances or outgassing physics, someone may have nudged them. It's a long shot, but long shots are how you treat a silent archive. All of this needs a big caution sign. Nature is an unembarrassed show-off. It makes straight dikes, lava intrusions, that run for kilometers. It lays down polygonal crack mosaics in drying mud that look like tiled floors. Impact shrapnel can mimic slag. Even industrial glass can be faked by lightning strikes, fulgurites, or meteor melt. That's why the rule, repeated like a mantra in planetary science, is no single line of evidence. You want converging oddities, geometry, chemistry, timing, and distribution, all pointing in the same direction. You also want a clean alternative hypothesis to beat, and for the beat to be decisive. So what would a sober search look like? You start remote. Sweep the moon with higher resolution imagers and synthetic aperture radar that can see through thin dust. Map glass compositions from orbit to flag patches with furnace-like signatures. On Mars, target lake beds and wind shadow traps where fine particles accumulate and stay put. Pull cores after we've mapped a chemical anomaly from the sky. On asteroids, prioritize metal-rich bodies and scan for repetitive microtopography. Bring home grams of surface dust to check for alloy grains that don't match meteoritic families. In cislunar space, inventory the faint zoo at Lagrange points and compare the clump's reflectance to known rock and metal. And in high orbits, run statistical searches for fragment swarms that look manicured, not random. Do we see any of this now? Know nothing that demands a technological explanation. The moon looks like the moon. Mars looks like a rusted geology department. And the asteroids look like they've been chewed by gravity and time, not by machines. That negative result matters. It constrains the past. If there was a prior solar system savvy civilization, it either didn't industrialize to the point of space infrastructure, stayed local and light, or lived so long ago that micrometeors and sunlight have erased the evidence to noise. But the search itself changes how we think. It reframes the question from were we first to where would the universe put the receipts if we weren't? It pushes us toward quiet archives and testable predictions. It turns romance into method, and it hands us a mirror. If we want our chapter to be legible 1,000,000 years from now, we now know where to write it, so a future reader, whoever they are, might still find the page. Geology is a witness with a bad memory, a field mapper joked to me once, kicking dust off a boot. Planetary geology, though especially on dead, airless worlds, has a better one. If there's a secret about us, or about someone before us, it may be waiting out there in the places where nothing happens, and therefore, nothing is forgotten. Rocks forget on purpose. Life forgets by accident. That's one way to frame the difference between the geologic record and the biological one. Stone is rewritten by pressure and heat. Cells are rewritten by reproduction. But there's a quiet hope tucked into biology that geology doesn't offer: heredity. DNA is a storage medium. It's lossy, noisy, always mutating, yet it carries information forward. If a civilization ever altered Earth's living systems in a serious, sustained way bred them, engineered them, redistributed them, could any trace of that show up as a lingering echo in genes, bodies, or ecosystems long after the tools and cities were gone? To chase that, we have to keep two ideas in our head at once. First, DNA is fragile on deep time scales. The actual molecules break apart. Even in the best freezers nature can offer, strands fragment until they're unreadable. That means we shouldn't expect to sequence a mysterious genome from 20 or 50 million, years ago the way we sequence a mammoths today. Second, evolution is a historian even when it burns its notes. Selection leaves patterns, bottlenecks, sudden expansions, sweeps where one variant takes over, and odd convergences where unrelated species arrive at the same solution. Those patterns are the echoes. Start with something familiar: domestication. When humans domesticated wolves into dogs, wild grasses into wheat, and aurochs into cattle, we left signature after signature in their genomes. Domesticated species show reduced genetic diversity compared with their wild cousins. Clusters of mutations around traits we prized: tameness, seed size, milk yield, and a curious package of traits called domestication syndrome, floppy ears, color variation, shorter snouts likely linked to shared developmental pathways. You can spot those patterns today, even without a single potsherd from the people who did the breeding. The organisms themselves remember, loosely. If someone else, long before us, had reshaped entire lineages, we'd expect some combination of these signs, scaled to their preferences. A planet that once farmed might carry many species with synchronized bottlenecks in parallel, trait-focused sweeps clustered in time. Of course, evolution can produce similar effects on its own. Ice ages compress populations and then release them. New niches spark radiations. Predators arrive and everything adapts. That's why none of these patterns by themselves can prove intent. But intent tends to cluster. It acts quickly and in the same direction across different species. A natural climate cycle won't care whether berry size, docility, and seed shattering all change in the same decade. A culture will. Engineering, if it ever happened here before, might leave different fingerprints. Modern synthetic biology sometimes recodes genomes, tweaking the codon usage, the three-letter units that spell amino acids, to make viruses less able to hijack cells or to harden organisms against errors. It sometimes inserts whole suites of genes at once, the way we might install an app. In theory, that can produce islands in the genome where many coordinated changes appear together rather than scattered by slow natural tinkering. It can also produce unusual patterns in the way DNA spells its proteins biased in ways selection alone would rarely prefer. Do those signatures persist across millions of years? The molecules don't, but the consequences can. An engineered metabolic pathway that truly improves survival may become indispensable, even when the precise changes are scrambled by time. The pathway's weirdness, its rarity, its distribution across species that shouldn't share it, could persist as a puzzle for biologists millions of years later. There's a subtler echo too: geography. Humans move species. We carry them to islands, continents, and biomes they would never reach on their own. The fingerprints of that habit are now everywhere: starlings in North America, rabbits in Australia, zebra mussels in the Great Lakes. Paleobiologists can see older versions of this in the fossil record. Sudden appearances of species in far-flung habitats without obvious land bridges or climate triggers. Most of the time, currents, winds, or shifting coastlines explain it. But a civilization leaves at different pattern clusters of arrivals, aligned with trade routes, resource needs, or a taste for the useful and the pretty. If we ever spotted an ancient pulse of long-distance transplants that made ecological, not geological, sense pollinators and their crops arriving together on multiple coasts, for example, that would be the sort of echo worth testing to exhaustion. Evolution writes in pencil, a geneticist once said. The eraser is mutation in time. To push past that, scientists read indirectly. They analyze selection landscapes that reveal how hard and how fast traits were pushed. They look for synchronized shifts across many lineages. They study transposon selfish DNA that copy and paste themselves around genomes, which can erupt in bursts during stress or when lab tinkering goes wrong. A wave of transposon chaos hitting dozens of unrelated species within a narrow window is a natural possibility during global upheaval. It's also what you might see after widespread bioengineering with imperfect containment. Again, not proof, but a flag. Ancient environmental DNA, the trace, fragments of genetic material shed into sediments and ice, extends our reach a bit. In lucky, cold, stable places, scraps can survive for hundreds of thousands of years, sometimes longer, offering a chorus of who lived here without bones or shells. If the chorus shifted abruptly, say, multiple domesticated forms replacing wild ones in the same decade across many distant lakes, that would look odd in a way mere climate change struggles to explain. It's still a short window compared with deep time, but it demonstrates a method. Listen for community-level harmonies and jolts, not single-species solos. What about the body as a ledger? Anatomy remembers too, in outlines. Domestication compresses faces. Flightlessness evolves on islands with no predators. Aquatic life converges on torpedo shapes. Those convergences are predictable. What would be less predictable is a burst of unnatural naturalness, a set of traits that track an aesthetic or practical logic across several species at once, and in many places, antlers and horns reduced simultaneously in multiple herbivores, or seeds and fruits swollen at once in unrelated plants, all within a narrow horizon. A breeder's eye creates symphonies, not isolated notes. There's a philosophical trap here we should step around carefully. It's easy to mistake our ignorance for someone else's intention. When we can't explain a pattern, the mind wants a mind behind it. That's why any bioecho hunt needs to carry skepticism as standard equipment. Natural selection is inventive. Microbes swap genes across species boundaries. Viruses edit genomes as part of their life cycle. Asteroid winters and volcanic summers can shove evolution hard enough to mimic 1,000 small human decisions. The test isn't, do we see something strange? It's, do we see many strange things pointing in the same direction at the same time with the same taste? Taste sounds slippery, but it can be operationalized. Humans prefer certain trade-offs: more yield, less aggression, easier harvest, brighter colors, sweeter flavors. A different civilization might prefer different things, but preferences cluster. If you found a deep time interval where edible tissues increased across plants with no obvious ecological driver, where docility rose across a handful of medium mammals without a matching predator change, and where those shifts were coupled to sudden range expansions that look like shipping lanes drawn on a map, you wouldn't have proof. You would have a hypothesis that refuses to go away. Let's be honest about the limits. Beyond a few million years, DNA's direct voice is essentially gone. Proteins decay, lipids weather, even pollen morphologies, often so distinctive they look like logos blur together. That pushes the genomic echo search toward the youngest edges of deep time, the borderlands where fossils and chemistry still speak clearly. Farther back, the best we can do is check that our explanations for big, weird biological events don't need extra minds. So far, they don't. The great transition cells absorbing other cells to become complex life. The bloom of the Cambrian, the colonization of land have muscular, if still debated, natural causes. Still, this exercise puts a mirror up to us in a new way. If we want to be legible to some future reader, the mistakes we're making, monocultures, genetic uniformity, synchronized vulnerabilities, are poor choices. Diversity is both a moral and a geological hedge. Life is an archive that prefers backups. A conservation biologist told me once. The more backups we keep, wild relatives, seed banks, genetic variety, the more chance some trace of us will make sense later, even if the USB sticks and clouds are long gone. If another intelligence ever walked this planet and touched its living things, the safest place to look for them isn't in bones or buildings. It's in patterns of change that feel coordinated against the grain of geology and ecology. Chemistry can whisper, rocks can hint, but life, even when it forgets the exact words, sometimes hums the melody. If Earth is a chalkboard that rewrites itself, then airless worlds are the notebooks nobody ever tears pages out of. No rain, no rivers, no plate tectonics. Just sunlight, silence, and dust. Planetary scientists have a simple saying for this. What doesn't breathe, remembers. The moon, asteroids, and a few quiet parking spots in space may be the best places to ask our wild question, safely. If a civilization came before us here or nearby, could any trace have slipped off Earth's restless surface and survived out there? Start with the moon. Think of the lunar regolith, the powdery soil, as a slow-motion tape recorder. Micrometeorites grind rock into dust. Solar wind implants particles. Each tiny impact flips grains, mixing like a spoon, but not too deep. Over long stretches, layers form that trap history the way snowfall traps seasons in an ice core. A lunar geologist once put it plainly, the moon is the museum of the inner solar system. If an earlier technological moment unfolded on Earth and then ended, direct artifacts here would be fragile and temporary. But dust is a gossip. During big asteroid strikes, Earth throws material into space. A tiny fraction lands on the moon. Most of that is just rock and glass. But if an impact struck near a dense human landscape today, fragments of concrete, metal, glass fibers, or melted electronics could hitch a ride. Over millions of years, those would weather, but some signatures could persist. Unusual alloy ratios, glass with chemical recipes that don't occur naturally, or microscopic laminates layered structures born of manufacturing, not volcanoes. Cold traps near the lunar poles make the case stronger. These are craters where sunlight never reaches. Temperatures are so low that volatiles, frozen gases, and organics can sit for geologic ages. It's a freezer with no defrost cycle, as one engineer jokes. If a prior industry ever leaked unusual gases into space, or if Earth's atmosphere briefly carried synthetic molecules at high altitudes during a deep past event, some fraction might have drifted outward and been sipped by the moon's shadows. That's not a promise of discovery. It's a testable place to look. Drill a few meters into an ancient, undisturbed patch, and you might read a ghostly environmental logbook, page after page of sun, dust, and whatever drifted by. Asteroids offer a different kind of shelf. Many are rubble piles, gravels held together by their own weak gravity. They evolve slowly. Space weather darkens them. Tiny impacts churn their surfaces. But their chemistry is simple, and that simplicity is a gift. If you find a lump with tidy, human-like alloying precise nickel-chromium ratios, trace elements in neat industrial patterns, or glass beads with cooling histories that scream furnace rather than fireball, alarms should ring. Geology is messy. A meteoriticist likes to say, manufacturing is tidy. That tidiness is exactly what we try to spot. Regularities too sharp for rock, too clean for volcanism. Even if no one ever built a machine in the asteroid belt, an Earth impact could seed it with odd fragments that wander for eons until some future probe plucks them from the dark. There's also the attic nobody checks. Gravitational eddies where objects can loiter for a very long time. The Earth-Moon system has Lagrange point-stable pockets where gravity balances out, like the quiet corners in a room where dust bunnies collect. The Earth-Sun system does too, and we already park telescopes there. If a civilization long ago ever dropped a probe, a platform, or even a bare metal truss in one of these hollows, it could outlast continents. Paint would chalk away. Plastics would embrittle, but fasteners, beams, or dense housings could persist as bare signatures shapes that aren't stream-rounded like natural stones, and that tumble or reflect light in ways rocks rarely do. An astronomer once called this the archaeology of light, because at first all you have is brightness changing over time as an object spins. If that brightness trace looks strongly non-natural flat facets, repeating edges, you go look closer. Skeptics will point out correctly that we've imaged the moon at high resolution and walked on it. Surely we'd have spotted anything obvious. But the lunar surface is 38 million square kilometers. Our best maps can see objects the size of a desk in some places, but not everywhere, and certainly not a meter down. Most of what could matter is microscopic or buried, core samples that read chemistry like a diary, not flags and footprints. The honest state of play is that we've taken beautiful photos and tiny bites. A paleotechnology, coring campaign sampling ancient, undisturbed soils at a handful of sites with different ages could change the question from dreamy to empirical. You don't go hunting statues? USA dust for non-natural polymers, industrial alloys, isotope ratios that look engineered, glass with cooling curves that match precise furnaces instead of random splashes. This isn't a call for fantasies. It's a way to discipline a big idea. If the Earth is a chronic amnesiac, you check the neighbor's doorbell cameras. The moon never blinks. It has been filming the neighborhood forever. Likewise, small asteroids are like the coin tray by your front door. Chaotic, yes, but honest about what passes through. And the Lagrange points are the coat pockets nobody empties. If nothing turns up, we still win. We learn to read airless bodies as archives, a skill we can export to other systems when we study exomoons or debris clouds around distant stars. There are practical wrinkles. Space radiation shreds plastics, so polymer signatures would be fragmentary at best. Micrometeoroid gardening mixes layers, so you need to model that churn to know how deep old really is at a chosen site. And there's always the temptation to see meaning in noise. An alloy that looks odd until you discover an exotic meteorite can make it. A shard of glass that screams factory until you measure its isotopes and find a volcanic origin. Nature is better at faking straight lines than we are at spotting fakes. A field geologist likes to remind students. That cuts both ways. We must expect false positives and be relentless about ruling them out. None of this assumes a moon base in the Jurassic. It acknowledges something humbler. Big impacts move stuff, dust remembers, and airless places don't tidy up. If a technological episode flashed briefly, anywhere in our neighborhood on Earth, on a lost moonlet, on an inner asteroid outpost, a measurable whisper might have settled into those quiet shells. Even if the only technosignatures we ever find are our own, laid down by Apollo descent plumes and specks of aluminum oxide from solid rocket exhaust, reading them in far future cores would teach tomorrow's scientists how to spot civilization in sediment, even when the civilization is long gone. There's a mirror here for us as well. If we want to be visible to distant airs without shouting, the elegant way isn't a monolith. It's a recipe. A short, unmistakable pattern embedded in long-lived material, repeated globally once and never again. An alloy ratio that never occurs in nature. A ceramic glaze with a deliberate prime number sequence encoded in layer thickness. Something small, durable, and kind to the future. We may never do this, but thinking about it turns the story from fear of vanishing to craft of how to leave a gentle, readable note in the universe's margins. For now, the Airless Archive invites simple, doable steps. Drill the moon a little deeper. Core the cold traps with clean tools. Pluck a few gram-sized pebbles from small, old asteroids and read them grain by grain. If all we find is silence, we'll have calibrated our ears. And if we ever hear a click that isn't geology, we'll have the methods in hand to ask the next question carefully. If the question is a campfire, this is where we stop staring at the flames and start laying out the trail mix. Speculation is fun. A plan is kinder. So let's turn the big what if into a to-do list you could hand to a geochemist, a mission planner, or a bored grad student with sturdy boots and better patience than most of us. The goal isn't to prove a lost civilization existed. It's to design clean tests that would have a chance, however slim, of catching the faintest echo, while improving our picture of Earth, whether we find anything or not. Begin with layers that behave like calendars. In lakes that freeze and thaw on schedule, sediment settles in annual bands called varves, thin, light dark pairs that are basically tree rings in mud. If intelligence ever nudged the planet hard in deep time, a lake varve stack gives you a way to measure how fast was fast. A sudden, human-like pulse, say, a sharp jump in heavy metals, or a razor-thin stripe of strange compounds would look different from the slower, fuzzy brush strokes of volcanoes or climate cycles. You'd core a handful of ancient lakes on different continents, date the layers carefully, and run the chemistry blind so the lab doesn't know which year is which. That blind step matters. It keeps hope from steering the results. Next are caves, which grow mineral draperies called speleothem stalactites and stalagmites. As they accrete, they trap whispers of the air, droplets, dust, trace gases. You can read them like slow poetry, line by crystalline line. If past air ever carried synthetic, molecules compounds that don't occur naturally, some of those might be locked in the carbonate matrix. We're not talking modern pollutants you've heard of. We're talking anything with peculiar halogens, chlorine or fluorine in odd arrangements, that nature almost never assembles alone. Start with caves far from modern contamination. Slice micrometers at a time. If you see a brief appearance, and this appearance of a synthetic fingerprint, tight as a stanza in stone, that's interesting. Not proof, interesting. Then there's the ocean's filing cabinet. Deep basins sometimes go low oxygen for long stretches. Geologists call those intervals anoxic events, periods when the seafloor preserves delicate material because bacteria can't easily chew it up. In those dark layers, we find exquisite records: pollen, soot, microfossils, even fallout from distant fires. Target a few such basins of different ages and pull long cores. What you're looking for isn't artifacts. It's patterns, fly ash-like spheres with industrial alloy ratios, glassy microspherules with cooling histories too tidy for random splashes, or mineral recipes that look engineered precise proportions that geology tends not to bake. As one lab veteran likes to remind new students, volcanoes are sloppy cooks. Manufacturing isn't. On land, scour ancient soils paleosols that were later buried and turned to rock. They carry the chemistry of old landscapes. Phosphate buildups where bodies decomposed or waste collected. Odd spikes of nitrogen from intense fertilization. Charcoal layers from controlled burning. Agriculture is a civilization's shadow visible even when the farmer is long gone. But you have to separate campfire smoke from lightning strikes. That means transects, straight-line sample paths, control sites, and a willingness to let most maybes stay maybes forever. All of that only gets you a few million years on good days. For older windows, you switch to what geologists call red clay in the open ocean sediments that accumulate painfully slowly, sometimes only millimeters per 1,000 years. That slowness is handy. It concentrates stray dust from everywhere. If any technological episode briefly sprinkled the skies with peculiar particles, this is where the planet would have been quietly catching them in a wide-mouthed jar. It's also where contamination is the enemy, so the workflow must be ceremonial. Clean rooms, blanks, empty control samples, and pre-registered protocols, public plans written down before you see data, so nobody can move goalposts after the fact. Meanwhile, the lab needs a technofossil index, a simple checklist of things that would rise above noise if they ever turned up. Non-natural polymers cross-linked in ways radiation shouldn't produce. Alloy ratios that require narrow temperature windows. Ceramics with layered structures encoding simple mathematics. Think prime gap thicknesses that geology wouldn't stumble into. None of these prove intention alone. But if 2 or 3 co-occur in the same thin slice, that's where eyebrows go up and new tests begin. Data science helps here, not for magic, but for humility. Feed large geochemical dataset scores from seas, caves, lakes into algorithms trained to spot pattern of patterns. combinations of signals that travel together in time and space. You're not asking the software to yell civilization. You're asking it to flag places where natural correlations break and tidy regularities appear. And humans do the slow, skeptical part. Track each flag back to the lab bench, replicate, attack it, try to kill it. If it survives, you widen the circle, new cores, new continents, different methods. Let's not forget the neighbors we just discussed. Airless archives. A lunar coring campaign that samples ancient, undisturbed regolith at several ages, plus a few drills into the moon's perpetual shadow freezers, would be a small, sharp mission with huge payoff. Add a modest survey of the Earth-Sun and Earth-Moon Lagrange points for odd, facet-rich tumblers, and a gram-scale sample returned from a very old small asteroid. None of this requires a silver screen spaceship. It's off-the-shelf rocket science and a careful shopping list. Every step above has a mirror step for skepticism. Could this be volcanic? Could this be a lab fingerprint we accidentally added? Is there a known microbial pathway that mimics this chemistry? You build those kill switches into the plan. Spike in tests where you secretly seed a few samples with known signals to see if the pipeline catches them. Keep teams honest. Independent labs get split samples. And because mystery loves a vacuum, you publish raw data early. Sunlight won't solve everything, but it keeps the story grounded and makes it harder for noise to dress up as signal. There's also a soft tool we shouldn't ignore: priors. In plain English, that's your starting assumption. Ours should be brutally modest. The chance that a pre-human industrial-scale civilization existed is low. The chance that its signals survived is lower. The chance we'll detect them is lower still. That may sound like a bucket of cold water, but it's how you avoid turning curiosity into certainty. A calm prior makes a faint bump in a graph stay a bump until it grows up into a mountain. What if we find nothing? Then we still win. We'll sharpen the picture of ancient climate jolts, refine timelines for past extinctions, and learn to read lake rings, cave lines, and sea pages with new finesse. We'll give future mission planners better reasons to drill, and we'll hand teachers better stories than "it was probably volcanoes." And if by some careful, replicable chain of evidence we do find something some thin, repeating chemical whisper that nature never learned to sing, then we start a different kind of work. Slower, more public, shared across disciplines. No big pronouncements, no racing to name the ghosts. Just the patient building of a case that can be broken, and if it can't be broken, will change how we see ourselves. There's one last kindness embedded in all this. We can practice leaving better clues for whoever comes after us. Not obelisks, recipes. Durable, biodegradable messages, encoded in ceramics, buried just deep enough to dodge weather, but shallow enough to be found by curious cousins. A glaze that spells out a simple pattern across layers. A tiny shard tucked in glacier ice with a primer etched in relief. Nothing boastful. Just a note that says, in the universal grammar of math and matter, we were here. You are not alone in having questions. In the end, this treasure map is less a map than a posture. Alert, but not breathless. Skeptical, but not cynical. We listen to rock and dust the way you listen to a sleeping house, aware that most creaks are just the wood settling, open to the chance that one of them isn't. And whether the night gives us silence or surprise, we'll have treated the question with the gentleness it deserves. This is the point in the story where all the loose threads have to choose a shape. We've wandered deep time, picked up clues that were more like whispers than words, and drawn a modest treasure map for how to look without fooling ourselves. Now we face the quiet, honest peak of the whole question. If the Earth did host another us, not identical, just intelligent enough to change the planet, would we recognize the echo? And if we wouldn't, what does that say about the kind of echo we're leaving? Think of everything we've learned here as a double mirror. On one side, the planet's habits. It buries, melts, grinds, subducts, dissolves tirelessly. On the other, our expectations. We look for straight lines, repeating angles, written signs, metals, and gloss. But the mirror reflects a mismatch. Earth's long memory is chemical, stratified, probabilistic. Our instincts are architectural. That's not a failure of imagination. It's just a reminder that the archive and the reader don't share a native language. So, step one at the summit is humility, the kind a geologist earns with dirt under their nails. The record is faithful, a stratigrapher once told her students, but it isn't complete. That single sentence threads this whole documentary. If a prior civilization burned, mined, smelted, cultivated, and discarded like we do, there's a sliver of a chance it wrote itself into clay and carbonate the way we're doing right now. If it lived lighter, wove its technology from perishable matter, or kept its numbers small, the odds collapse. Absence of proof. Here is less a verdict and more a property of the library. Step two is the recognition that our search already made us better readers. Whether the shelf is empty or not, we now know which pages to scan. Varved lake beds, cave draperies, anoxic sea muds, old red clays, buried soils. We know which questions to keep in our pocket. Is this spike sharp enough? Is this alloy too tidy? Does this layer travel around the world? And we know how curiosity can trick us, why blind analyses, replication, and independent labs are kindnesses, not red tape. Even if we never meet a stranger in the strata, we'll have learned to hear our own footprint with more clarity. Step three is the gut-level realization that our maybe carries weight either way. If we find nothing, no synthetic polymers in ancient speleothems, no unnatural alloy spherules in 70-million-year-old clays, no pan-continental coincidence of chemical oddities, then we live with a beautiful, teachable uncertainty. We're likely first at this scale on this world, at least in the slice we can raid. That's not a victory lap. It's a responsibility upgrade. First writes the template. First sets the standard for how legible a civilization should try to be, both to its own descendants and to anyone who arrives after a long winter of forgetting. If we do find something, if a careful chain of labs survives every attempt to break it, then the peak gets sharper. We won't get names or faces or myths. We'll get a signature, a thin, global line whose chemistry doesn't fit nature's known recipes. At that moment, the question stops being, were we first? And becomes, how many times does intelligence bloom on a good planet? It also becomes, how do we treat each other, knowing we're part of a lineage we didn't expect? Suddenly, our timeline expands sideways. We aren't a solitary spark. We're a verse in a longer poem. Either way, the same practical wisdom flows downhill. The most durable gifts a civilization can leave aren't monuments. They're readable disruptions, signals that remain interpretable without context. We've named a few. Isotope excursions with artificial ratios, stubborn technofossils, synthetic molecules that do not evolve in wild chemistry. There's a softer class too, patterns etched into matter that any curious mind could decode. Simple primes and layer thicknesses, ratios of geometry baked into ceramics. A tiny Rosetta chain of numbers at multiple scales so redundancy survives when the object doesn't. Not advertising, orientation. It also means we can stop treating the search like a verdict and start treating it like stewardship. Our own house has levers we can still pull, reduce the noise we pour into the record while strengthening the legibility of the few marks we choose to keep. That sounds abstract, but it's practical. One day, when the lights are off for reasons we hope are gentle, the layers we've already laid down will be the only introduction we get. What do they say? Right now they say sharp carbon, scattered plastic, a brief flicker of radiation, a dip in biodiversity. A future core reader would understand power from that. They might struggle to see wisdom. Here's a different way to put the climax in your ear. Imagine two tables in a lab. On one, a lake core with a thin, puzzling band. On the other, a ceramic shard recovered from a vault under polar fern, glazed with alternating lines you can measure into primes with a ruler. The first table makes your heart race. The second slows it down. One is a mystery. The other is a message. Both could belong to us. Only one takes care of the reader. The same symmetry applies to our outward reach. If moons and small asteroids are the solar system's safety deposit boxes, then a modest set of missions clean drills in ancient lunar regolith, a sweep of Lagrange points for engineered tumblers, a gram of dust from a very old rock becomes our way of asking the question with better manners. Quiet, precise, open data. If nothing turns up, we've still taught ourselves how to read whisper archives. If something does, we'll be grateful we learned not to shout. Let's also dare a moral in plain speech. This story began with a headline-shaped hook. What if we weren't first? Because that's how you invite sleepy curiosity to the table. But the center of the story isn't competition. It's continuity. If Earth can host thinking twice, it can probably do it again. The most meaningful thing we can do with that possibility is make the planet kinder for the next verse, whether the singer is our great grandchildren, or a species we'll never meet. Cleaner water, thicker biodiversity, slower, steadier energy. If we think of those choices as leaving a better baseline for the next reader, the climate graphs stop being scolds and start being love letters to whoever inherits the sediment. A few small grounding truths belong here at the crest. Time is not a trash can, a paleoclimatologist told us in an interview cut for Time. It's a ledger. What goes in doesn't disappear. It's just accounted for differently. That ledger is what we've been reading together. It is also what we're writing into every day. Extraordinary claims don't need extraordinary tone, a geochemist said when we asked how to discuss anomalies in public. They need ordinary procedures done extraordinarily well. That's what our practical map was. Not a rabbit hole, just a checklist with clean gloves. And from a cave scientist who spends her life reading stone rain, the Earth is patient. If we are too, it will tell us what it can. That's the softest, truest line in this whole hour. Now, at the top, the view is wider than the question that brought us here. We can see how easily the past is smoothed, how little of us will harden into clues, and how much kindness there is in a plan that looks for faint signals without forcing them to be something they're not. We can also see a simple inversion that makes the documentary more than a thought experiment. Even if no one ever came before, someone will come after. Search as if to meet the first. Leave as if to welcome the next. So the sharp edge of maybe isn't a cliff. It's a tuning fork. Strike it and two notes ring. Wonder and duty. Wonder sends you to lakes, caves, seas, and moon dust with patient eyes. Duty sends you to city halls, farms, schools, and workshops with gentler hands. The same mind can hold both. If you're listening in bed and your thoughts are beginning to slow, that's okay. This is a cozy summit. There isn't a dramatic reveal waiting around the bend, just a gentler way to hold the question. Are we first? We don't know. Will we make it easier for the next researchers of any species to find out? That part is up to us, and it can start tomorrow, ankle deep in a muddy lake, or right now, in the choices that shape the little line we're writing into stone. When you tilt your ear to the Earth's ledger, what you hear isn't a verdict, it's a pulse. Layer, layer, layer. A beat that goes on whether we're here to count it or not. And tucked between two of those layers thin as a breath, there's our verse. Brief, bright, and, if we're careful, kind. If you've stayed with us to this quiet edge of night, thank you. We began with a single, slightly mischievous question. What if our Earth wasn't the first to host a civilization? And followed it through rock, water, chemistry, and myth. Along the way we learned that Earth is a tireless editor. It buries. It melts. It scrapes and rewrites. It keeps a ledger rather than a library. And most entries are written in the ink of isotopes, not in letters or monuments. It doesn't make the past unknowable. It just makes it patient. In that patience, we also learn something about ourselves. We tend to imagine intelligence as a skyline, metal, glass, light. But the deepest record doesn't care about skylines. It remembers ratios carbon to carbon, oxygen to oxygen, strange molecules that don't belong, and sudden changes that travel around the world. If a prior someone burned, smelted, mined, and farmed at scale, Earth might still hold a thin line with their name burned into it, not in words but in chemistry. If they chose a lighter touch wood in fiber, song in memory, their chapter may have faded into the slow drift of sediment and time. That's the humility piece, and it's a gift. As one stratigrapher likes to tell first-year students, the rock record is faithful, but it isn't complete. We can honor that by asking better questions instead of louder ones. Where would a readable signal hide the longest? In varved lake beds where each layer is a year. In cave draperies that trap aerosols like slow rain. In anoxic seafloor clays where oxygen can't gnaw the story away. On the moon where there is no weather, no plate tectonics, only time and dust. We also arrived at a practical map. If you go looking, go with clean hands. Use blind labs and independent replication. Hunt for patterns that repeat across continents, not curiosities in one quarry. Prefer chemistry over architecture, narration over drama, and context over headlines. If you find an anomaly, don't sell it, stress test it. As a geochemist told us off camera, extraordinary claims don't need extraordinary tone. They need ordinary procedures done extraordinarily well. That's the standard any real discovery will have to clear. And if we never find a prior us, that answer is meaningful too. It would suggest that on this world, at this scale, we might be first, at least in the fraction of Earth's memory we can still read. First sounds glamorous. Really, it's heavier. It means the template is ours to set. It means we can choose what kind of signal we leave for the next curious mind that pulls a core and wonders about the thin, bright band with our fingerprints in it. Right now, our line says, sharp carbon spike, scattered microplastics, a flicker of artificial radionuclides, a dip in biodiversity. A future reader would understand power from that. They might not immediately hear wisdom. We can still tune the note. Cleaner energy that doesn't carve a scar into the ledger. Materials that either vanish kindly or persist on purpose with a message. Land use that thickens biodiversity instead of thinning it. These aren't just environmental choices. They're editorial choices about how our chapter reads in deep time. There's a gentler idea tucked inside all this. The best legacy isn't a monument. It's legibility. If you wanted to leave one kindness to whoever reads this millions of years from now, it could be redundant, context-free patterns any mind could decode. Primes etched into ceramics that fossilize. Ratios encoded in layer thicknesses. A short, universal Rosetta, baked into multiple materials and tucked into multiple environments: stone, glass, ice, so at least one survives. Not advertising, orientation. And then there's the outward look. If small, airless worlds are the solar system's safety deposit boxes, we can ask our big question with good manners beyond Earth. Sample ancient lunar regolith for engineered. Alloys that nature doesn't make. Sweep the Lagrange points for objects in suspiciously stable, non-natural orbits. Bring home a gram of dust from a truly old asteroid and check it, grain by grain, for synthetic residues. If nothing turns up, we've still learned to read whispers. If something does, we'll be grateful we practiced patience. Even if the answer is permanent silence, the habit of listening changes us. We stop treating history like a trophy case and start treating it like a conversation with time. We learn what our own marks mean while we can still alter them. We grow a little softer toward uncertainty. And we make room for wonder without letting it run ahead of evidence. Before we dim the lights, a few lines worth keeping in your pocket. Time is not a trash can. It's a ledger. What we throw away becomes someone else's data. Absence of proof isn't proof of absence, but it is a nudge toward humility. That's not a loophole. It's an ethic. The Earth is patient. If we are too, it will tell us what it can. Patience isn't passive. It's disciplined curiosity. So here's your bedtime thought experiment, simple and specific. If you could leave one message in stone for a reader 10 million years from now, and you only get 12 words, what would you write? That's our comment prompt tonight. Share your 12-word message below. I'll pin a few that capture both clarity and kindness. If writing isn't your thing, share which trace you think would outlast us. A ceramic shard, a cave layer, a lunar grain of dust? And if you enjoyed traveling this path at the speed of plate tectonics, you can help this sleepy little signal reach other curious minds. Tap subscribe, leave a like so the algorithm knows to show this to night owls and daydreamers. And tell a friend who loves big questions asked softly. It genuinely helps. For next time, choose our next mission. Should we comb the moon for time capsules in the oldest dust? Should we follow a single isotope, say, carbon-13 through 3 mass extinctions to see what stories it tells? Or should we explore an Earth we don't often picture? The 1 billion years in the future. And what of ours, if anything, could still be legible then? Drop your pick in the comments and add a line about why. However the votes fall, we'll keep holding wonder and rigor in the same hand. We'll keep speaking plainly. We'll keep the tone human-scaled and unhurried, because big questions don't need big noise to feel big. They need space. If you're listening in the dark, let the world get quiet now. The planet will keep turning its pages, whether we're awake to read them or not. Somewhere, a lake is laying down tonight's paper-thin layer. Somewhere, a cave is catching a dust mote that won't move again for centuries. Somewhere on the moon, nothing at all is happening, and that stillness is its own kind of archive. Close your eyes if you can. Breathe once with the idea that we might be first. Breathe again with the idea that we might not. Either way, we have this small exact now, the chance to leave a kinder line in the stone. Sleep well, time traveler. And when you wake, if the question is still with you, bring it back. We'll be here, same gentle pace, same faithful ledger ready to turn the next page together. If this resonated with you, consider subscribing. Leave your 12-word message for the future in the comments, and tell us which mission we should take on next. Lunar time capsules, isotope storytelling, or the far future Earth. Your ideas shape this show.